Imagine you are watching a live concert through your phone. The camera zooms in. You can almost feel the vibration of the drums, and your friend sitting in another city is watching the same moment without any delay. This kind of seamless experience is what modern wireless communication strives for. Today, we are going to explore how 5G and 6G technologies are transforming the way we connect, communicate, and experience the world. So, let's dive into this slide titled, "What are 5G and 6G?" and see how these two generations of wireless systems compare and evolve. The key idea here is simple. 5G gave us high speed and low latency, but 6G takes this even further, reaching toward a fully intelligent, immersive, and automated communication era. Let's begin with the first key point: faster and more reliable communication. Think of 5G as building a superhighway for data. On this highway, your information travels at lightning speed, far faster than in previous generations. While 4G offered speed suitable for streaming high-definition video, 5G can handle ultra-high definition or even real-time virtual reality without interruption. The reliability also improved dramatically. Imagine if every car on the highway had its own lane with no traffic jam. That is what 5G does through its efficient spectrum allocation and error control. Now, 6G is like transforming that superhighway into a teleportation system. It aims for data rates up to 1 terabit per second and latency as low as 0.1 millisecond. In simple terms, that means data moves almost instantly from one device to another. This level of performance is not just about watching videos faster. It enables entirely new possibilities like remote surgery or instant coordination among autonomous vehicles. The reliability goal of 6G, often described as 7 nines, means the system is available 99.9999% of the time. It is like having electricity that almost never goes out. This extreme reliability makes 6G a foundation for mission-critical applications where even a millisecond delay could be disastrous. Moving to the second point, enhanced user experiences and new applications. 5G already supports smooth real-time interactions, improving video streaming, gaming, and remote work. It feels like moving from watching a movie to stepping into it. The network latency is so low that when you move your controller, the action happens instantly on the screen. Now imagine 6G extending this experience to a new dimension. With 6G, communication will not just transmit data, it will transmit perception. Think of it like adding a sixth sense to the internet. Holographic communication could allow you to project your 3D image in real time to a meeting room on another continent. It also enables what we call tactile internet, where you can feel the texture of a material remotely through haptic feedback. These experiences depend on massive data transmission and extremely stable connections, both of which 6G is designed to deliver. So, if 5G connected people, 6G will connect intelligence, creating networks that can sense, learn, and adapt to users. Next, let's discuss the third aspect illustrated on the slide: energy efficiency and sustainability. You might wonder, with higher speeds and more devices, won't energy consumption explode? Interestingly, both 5G and 6G aim to improve energy efficiency. Think of your phone battery as a fuel tank. In 4G, this tank emptied quickly during heavy data use. In 5G, optimization techniques like beamforming and network slicing make data transfer more efficient, like cars using cruise control to save fuel. 6G goes even further by targeting a 20-year battery life for certain low-power devices, especially in massive IoT networks. It will rely on technologies such as ambient backscatter, which allows devices to communicate by reflecting existing radio waves instead of generating their own signal. It is as if tiny sensors could whisper to each other using the echoes of existing sounds without shouting and wasting energy. This focus on sustainability is crucial because by the time 6G is widely deployed, we might have tens of billions of connected devices, all sharing limited energy resources. Now let's move on to the fourth dimension of evolution: precision and density. 5G already supports a high density of devices, up to about 1 million per square kilometer, enabling smart cities and connected factories. Imagine a busy train station where every person is talking on the phone, streaming music and navigating with maps, yet the network still runs smoothly. That is the promise of 5G capacity. 6G will push this even further, targeting 10 connected units per square meter, which means an environment saturated with sensors, cameras, and micro devices all communicating seamlessly. More importantly, 6G introduces centimeter-level positioning accuracy. To understand this, picture a swarm of drones delivering packages. With 5G, the network can tell where each drone is within a few meters. With 6G, it knows the exact position within a few centimeters, allowing precise coordination and collision avoidance. This kind of accuracy transforms industries like autonomous driving, logistics, and smart manufacturing. It makes communication networks not just fast and reliable, but also spatially intelligent. Between these points, we can see a clear pattern. Each generation does not simply make the previous one faster. Instead, it changes the very nature of connectivity. 5G expanded our ability to interact in real time, while 6G will allow machines and humans to interact almost as if they share the same brain. You can think of it as the difference between conversation and telepathy. 5G allows smooth conversation with little delay. 6G aims to synchronize thoughts, actions, and decisions across the network through AI-driven optimization and integrated sensing. This convergence of communication, computation, and intelligence marks the true evolution from 5G to 6G. Before we wrap up, let's briefly revisit the key metrics shown on the slide. 6G targets up to 1 terabit per second data rate, latency as low as 0.1 milliseconds, 7 nines reliability, and centimeter-level accuracy. It also aims for 20-year battery life and ultra-high density connectivity. Each of these metrics represents not just a number, but a technological leap that requires innovation in spectrum use, hardware design, and network architecture. These goals will push research into new frequency bands like terahertz waves and explore novel technologies such as intelligent reflecting surfaces and quantum communication interfaces. To conclude today's discussion, 5G and 6G represent more than just faster internet. They are milestones in our journey toward a fully connected and intelligent world. 5G laid the foundation with speed and stability, while 6G will build upon it with awareness and intelligence. Together, they illustrate how communication engineering continues to evolve, not just solving technical problems, but shaping the way society functions. As future engineers, your challenge will be to take these principles and imagine what comes next. Maybe one day, you will design the system that makes 7 a reality. But for now, remember this: 5G connected our world. 6G will make our world think. Imagine this. You are trying to stream your favorite movie on a crowded subway, but the video keeps buffering, or your online game freezes right at the moment of victory. These small frustrations tell us something important about our communication systems. They are reaching their limit. So today, let us explore why we actually need 5G and 6G. Not just as faster versions of what we already have, but as essential technologies to meet the growing needs of modern society. The title of this slide is simple. Why do we need 5G and 6G? The answer is that current technologies cannot keep up with the massive demand for speed, connectivity, and reliability that both our personal lives and industries now depend on. Let us start with the first key reason: the increasing demand for high-speed data. Think of data as water flowing through a pipe. As our digital lives expand, we are trying to push more and more water through a pipe that was originally built for a smaller flow. Streaming 4K videos, playing cloud-based games, or handling real-time data from thousands of sensors requires an enormous amount of bandwidth. The old 4G networks are like narrow pipes, while 5G expands that pipe several times over, and 6G aims to turn it into a high-pressure water system where information flows almost instantly without leaks or delay. This demand is not just about entertainment. Businesses rely on real-time analytics, autonomous systems, and cloud computing that all need extremely fast and stable connection. Without faster networks, our progress would be like trying to fill a swimming pool with a garden hose. So 5G and 6G are not luxuries, they are the infrastructure that allows innovation to continue. Now let us move to the second point, the growth of connected devices and services. Look around you. Your smartwatch, your car, your refrigerator, even your streetlights can now talk to the internet. This massive network of smart devices is what we call the Internet of Things. It is like a giant digital ecosystem where every organism constantly exchanges information. The challenge is that our current networks were designed for a world with millions of connections, not billions. Imagine a highway system built for bicycles now crowded with trucks, buses, and cars all moving at once. It quickly becomes congested and inefficient. 5G introduced technologies like massive MIMO and network slicing to manage these simultaneous connections more efficiently, but 6G takes it even further. It aims to create an environment where communication among billions of devices feels as seamless as conversations among a few friends in a quiet room. This will be essential for future cities, autonomous transportation systems, and industrial automation, where machines must coordinate perfectly in real time. While speed and connectivity are central, we should also consider the third reason, the integration of artificial intelligence and advanced services. As you can see in the illustration, AI sits at the center of modern communication. Think of it as the brain of the network. In traditional systems, the network only follows instructions. It reacts. But 5G, and especially 6G, are designed to think, to anticipate user needs, and to optimize performance in real time. It is like moving from a passive road that cars drive on to a smart road that guides each car toward the smoothest path while preventing accidents. For example, AI can predict which cell tower will handle your signal best as you move, reducing latency and improving reliability. In 6G, intelligence will be deeply embedded in every layer of the network, from the physical radio channels to the core data management. This intelligence is crucial because the complexity of managing billions of connected devices is beyond what traditional human-controlled systems can handle. So, AI will not just support the network, it will become the network's nervous system. Finally, let us talk about the fourth motivation, the demands of modern industries and daily life. In the past, communication technology was mainly about personal convenience. Today, it underpins critical sectors like healthcare, transportation, and manufacturing. Imagine a surgeon performing a remote operation from hundreds of kilometers away. A delay of even a fraction of a second could be catastrophic. Or consider self-driving cars navigating through busy streets. They must communicate with each other instantly to avoid collision. These applications demand reliability and latency far beyond what 4G can provide. 5G begins to meet these needs with ultra-reliable, low-latency communication, while 6G will take this reliability to an almost perfect level. It is like moving from a manual car that sometimes stalls to an autonomous vehicle that never loses control. The same applies to smart factories, where thousands of robots work together like a synchronized orchestra. Only with 5G and 6G can we ensure that every instrument plays in perfect timing. As we connect these four ideas together, a clear picture emerges. The transition to 5G and eventually 6G is not driven by marketing or competition among phone companies. It is driven by necessity. Our digital world is growing faster than our networks can handle, and every new service we invent pushes the limits of what is possible. High-speed data is the fuel, connected devices are the passengers, AI is the driver, and industry applications are the destination. Without improving the road itself, none of these can move forward efficiently. 5G expands the road, and 6G turns it into a smart, self-managing expressway. To summarize today's discussion, we need 5G and 6G because the world is evolving toward real-time, intelligent, and interconnected communication. 4G brought us the mobile internet, 5G brings us connected intelligence, and 6G will bring us ambient intelligence where connectivity becomes invisible and omnipresent. These technologies are not just about faster download speeds. They're about enabling a society where everything and everyone can communicate seamlessly, securely, and efficiently. As engineers, your task will be to design systems that balance performance, reliability, and sustainability. So, the next time you experience lag while streaming or notice your devices struggling to connect, remember that these everyday moments are the reason we keep pushing wireless technology forward. 5G and 6G are not the end of the journey. They are milestones on the path to a truly connected world. Imagine you are attending a live sports game through a VR headset. You turn your head to follow the ball, and the image updates instantly, almost as if you were there. But if the network delays even slightly, the experience breaks, and your brain feels the mismatch. That smooth, real-time experience depends on how our networks are built. This brings us to today's topic: why choose 5G SA over NSA? The key idea is that 5G standalone, or SA, offers something its predecessor, 5G non-standalone, or NSA, cannot fully deliver. It provides advanced features like network slicing, ultra-low latency, simplified architecture, and improved cloud support that are essential for the next generation of digital services. Let's explore why operators and engineers are shifting towards SA and how it represents the true potential of 5G. The first major reason is network slicing capability. Imagine a highway where all types of vehicles share the same lanes. Trucks, buses, motorcycles, and ambulances are all stuck in the same traffic. That is how traditional networks work, sharing the same resources for every type of user and application. Network slicing changes that. It allows us to create multiple virtual lanes, each dedicated to a specific service with its own speed and priority. For example, one slice can handle autonomous vehicle communication with ultra-low latency, another can support video streaming, and another can connect industrial robots. In 5G SA, this slicing is built into the core of the network, while in NSA, it is only partially implemented because NSA still depends on 4G infrastructure for control signaling. About half of global operators prioritize SA precisely because it enables this flexibility. It is like giving emergency vehicles their own private lanes, so they never get stuck in traffic, ensuring critical communication always runs smoothly. Moving to the second point, ultra-reliable low-latency communication, or URLLC. Latency is the time delay between sending a signal and receiving a response. You can think of it as the reaction time of a network. In NSA systems, that reaction time is limited because part of the network still relies on the older 4G control plane. It is like having a high-performance sports car that must still use a dirt road to reach the highway. The potential is there, but the path slows it down. In contrast, a fully independent 5G network with an optimized 5G core allowing end-to-end latency to drop below 1 millisecond. This is critical for real-time applications such as remote surgery, autonomous vehicles, and industrial automation. In these cases, even a tiny delay can cause major problems. With URLLC, communication becomes as instantaneous and dependable as a reflex in your body. It is not just fast. It is predictable and consistent, which is essential when machines must respond faster than human perception. Now let us look at the third advantage, simplified network architecture. Think of NSA as a two-story building where the ground floor is 4G and the upper floor is 5G. Every time data travels, it must go through both floors, which complicates coordination and increases the chance of bottleneck. That removes the dependency on 4G, creating a single, unified structure designed entirely for 5G. This simplification reduces latency, improves efficiency, and makes the network easier to manage. It is like renovating an old house built on mismatched foundations versus constructing a new one from scratch with modern materials. Operators appreciate this simplicity because it leads to faster deployment of new services and easier integration with AI-based network management tools. When the architecture is clean and coherent, we can innovate more quickly without being constrained by legacy systems. The fourth point relates to improved cloud support and scalability. In today's connected world, almost every service depends on the cloud, from online gaming to industrial control systems. Traditional NSA networks struggle to deliver consistent cloud connectivity because of their hybrid nature. SA, however, is designed with cloud-native principles, meaning that network functions can be virtualized, distributed, and scaled dynamically as needed. Imagine running a restaurant where every time more customers arrive, your kitchen automatically expands and hires more chefs. That is how cloud-native 5G SA operates. It allocates resources on demand, ensuring that no user experiences congestion. This tight integration with cloud environments also enables edge computing, where processing happens closer to the user, further reducing latency and improving reliability. For industries adopting automation or AI-based services, this flexibility is vital to handle massive data streams without overloading the core network. Between these points, we can see how 5G SA transforms not only the performance, but also the philosophy of wireless communication. NSA was a necessary stepping stone, a bridge helping us transition from 4G to 5G. But it still carries the limitations of its predecessor. SA, in contrast, represents the full maturity of 5G technology. It is like moving from a hybrid car that still burns gasoline to a fully electric vehicle optimized from the ground up. Benefits of network slicing, URLLC, simplified architecture, and cloud integration all combine to create a system capable of supporting future applications we have not even imagined yet. Before we conclude, it is worth noting that this shift is not just theoretical. According to surveys, around 50% of network operators now prioritize SA for its advanced slicing capabilities, and about 30% emphasize its ultra-reliable low-latency communication feature. These priorities highlight the growing recognition that SA is the key to unlocking the full promise of 5G. As more industries depend on real-time, data-intensive, and automated systems, the demand for SA networks will only increase. To summarize today's discussion, 5G SA stands out over NSA because it delivers independence, intelligence, and innovation. Network slicing allows tailored services for different users. URLLC ensures instant and reliable responses. Simplified architecture enhances efficiency, and cloud-native support enables scalable, adaptive network. Together, these features mark a turning point in wireless communication. As future engineers, you will be the ones designing, optimizing, and maintaining these systems, ensuring that our connected world continues to evolve smoothly. So the next time you see the term standalone in a technical paper, remember it means much more than just a label. It represents the true freedom and capability of next-generation networks that will shape the future of communication. Imagine you're using your smartphone to make a video call with someone across the world. The image is clear, the sound is crisp, and there's no delay. You probably never stop to think about who made this possible, who ensures that your phone, no matter the brand, can connect seamlessly to another device built by a different company in another country. This invisible harmony of communication brings us to today's topic: who develops 5G and 6G networks? The key message here is that no single company or country builds these networks alone. Instead, global collaboration among tech companies, governments, and international organizations ensures that 5G and the future 6G can operate smoothly and consistently across the entire world. It is a massive orchestra where every instrument must play in tune, following the same sheet of music. Now, let us explore how different players contribute to this grand symphony of wireless innovation. First, let us talk about the major companies involved. The development of 5G and 6G is not led by a single entity, but by several technology giants like Qualcomm, Ericsson, Nokia, and Huawei, each contributing its expertise. You can think of them as the engine makers of the telecommunications world. Qualcomm, for example, focuses on chipsets and signal processing technologies that make devices more efficient. Ericsson and Nokia provide network infrastructure, like the cell towers and antennas that carry your data. Huawei has invested heavily in research on signal optimization and high-frequency communication. Their combined efforts drive the global rollout of these networks. Imagine these companies as architects building a massive digital city. Each one designs a specific part, but all their designs must fit together perfectly to make the city functional. Without their collaboration, the network would be fragmented, with devices unable to communicate seamlessly across different systems. Moving on, we have the second key group, the international standards organizations. These include groups like 3GEP, ITU, and IEA. If the companies are the builders, these organizations are the rule makers. Their job is to define how devices and networks should communicate so that everyone follows the same blueprint. 3GEP, or the Third Generation Partnership Project, creates the technical standards that define 5G architecture and functions. ITU, the International Telecommunication Union, manages global spectrum allocation, deciding which frequency bands can be used for mobile communication to avoid interference. IEEE, the Institute of Electrical and Electronics Engineers, sets rules for related technologies like Wi-Fi and Ethernet. You can think of these organizations as referees in a sports game. They make sure all players follow the same rules so that the game remains fair and consistent. Without them, each company might create its own incompatible system, leading to chaos where your phone might only work in one country but not another. Now let us consider the third essential force behind these developments: governments and policymakers. Technological innovation alone is not enough. It must align with national regulations, funding programs, and long-term infrastructure planning. Governments play a crucial role in spectrum licensing, cybersecurity policy, and investment in research and education. Think of them as city planners who decide where roads will go and how traffic lights should operate. For instance, when a country decides to auction its frequency bands, it shapes the future of how 5G and 6G services will grow. Some governments, such as those in South Korea, the United States, and Finland, have already launched national 6G initiatives to stay at the forefront of innovation. These efforts not only push technology forward, but also ensure economic and security interests are protected. In essence, while companies invent and build, governments provide the framework and resources that make deployment possible. Finally, we must not forget the role of collaboration and research partnerships among academia and industry. Universities and research institutes serve as the laboratories of future communication systems. For example, many breakthroughs in antenna design, signal modulation, and terahertz communication originated from academic research long before reaching the market. You can imagine this collaboration as a relay race. Researchers run the first lap by discovering new principles and publishing them in paper. Companies grab the baton, transforming those ideas into practical products. Then standardization bodies refine the rules so everyone can adopt them safely and consistently. This cycle repeats with each generation of wireless technology. Without strong collaboration between theory and practice, the progress of 5G and 6G would slow dramatically. Taiwan, for instance, contributes through its semiconductor industry and university labs, playing an important role in global research ecosystems. When we look at these four forces together, a clear picture emerges. The development of 5G and 6G is not a competition, but a coordination effort on a global scale. Companies innovate, organizations regulate, governments facilitate, and researchers illuminate the path forward. It is like building a massive international bridge that connects every corner of the digital world. Each participant brings a different skill set, and the structure stands only when all parts align. To summarize, 5G and 6G networks are shaped by the combined efforts of leading technology companies, international standards organizations, governments, and research institution. Qualcomm, Ericsson, Nokia, and Huawei push technological boundaries through innovation and investment. 3GAP ensure that everyone speaks the same technical language. Governments guide development through regulation and funding, while academia contributes the foundational science that drives new discovery. Together, they form an ecosystem that makes global communication possible. So the next time your phone connects instantly to a network while traveling abroad, remember that it is not just technology working behind the scenes, but the result of years of collaboration among thousands of engineers, researchers, and policymakers around the world. 5G and 6G are not simply technologies. They are the product of a unified global effort to keep humanity connected in an increasingly digital era. Imagine you are boarding a high-speed train. At first it starts smoothly, picking up speed as it leaves the station. The train represents the evolution of wireless network. We have already boarded the 5G train, but ahead of us lies another station called 6G, where the journey continues even faster and farther. Today's topic is when will 5G and 6G arrive. The key message of this slide is that 5G is already here and expanding rapidly, while 6G is expected to emerge around 2030 with research and early testing already in progress. These transitions do not happen overnight. Each generation of wireless technology takes years of preparation, experimentation, and standardization before it becomes part of everyday life. Let us look closer at how far 5G has come and how the world is getting ready for 6G. Let us begin with the first point, the current state of 5G. Since 2020, major countries such as the United States, China, and South Korea have aggressively rolled out their 5G network. You can think of this rollout as laying down a new highway for digital communication. Every new smartphone or IoT device released today is like a new vehicle designed to run efficiently on that highway. The difference is striking. With 4G, the world could stream videos and use cloud apps comfortably. But with 5G, the data speed and capacity are so much greater that it enables entirely new experiences like real-time virtual reality and smart city automation. Nearly all flagship phones today are 5G ready, and industries from manufacturing to healthcare have started adopting private 5G networks for mission-critical operation. The infrastructure expansion is similar to building a power grid during an industrial revolution. Once the lines are connected, innovation follows naturally. However, the real magic of 5G lies not only in speed, but in reliability and the ability to handle millions of devices simultaneously. Something 4G could never achieve at scale. Moving forward, let us talk about the global momentum driving 5G adoption. It is important to understand that communication networks do not grow evenly across the world. Developed nations often lead in deployment, while others follow as costs decrease and technology matures. Think of it like the spread of electricity in the early 20th century. At first, only large cities had power, but eventually it reached every village. Similarly, 5G coverage is spreading rapidly, with more than 80 countries now offering some form of service. Governments and telecom companies continue to invest heavily because 5G serves as the backbone for digital economy. Cloud computing, remote learning, autonomous vehicles, and industrial robotics all rely on the low latency and high reliability that only 5G can provide. As adoption grows, economies of scale make the technology more affordable, accelerating its global reach. By 2025, 5G is expected to become as common as 4G is today, connecting billions of users and devices seamlessly. Now let us look ahead to the preparations for 6G. If 5G is the high-speed train we are riding today, 6G is the Hyperloop being designed for tomorrow. Organizations like ITU, 3GAP, and leading technology companies have already started defining what 6G should achieve. The goal is not just higher data rates, but also smarter, more adaptive networks that integrate artificial intelligence directly into their operation. This preparation phase is like designing a city of the future. You do not simply add taller buildings. You rethink the layout entirely to make it more efficient, sustainable, and intelligent. Research labs in countries such as Finland, Japan, and the United States are already running early 6G experiments using terahertz frequencies and intelligent reflecting surfaces. These technologies could deliver speeds up to 1 terabit per second and reduce latency to nearly zero. The work being done today will shape the standards that define 6G around 2028, paving the way for commercial deployment by 2030. Finally, let us discuss what this timeline means for us as engineers and users. The shift from one generation to the next is never abrupt. Instead, it is a gradual layering process where 5G continues to improve while 6G research matures in parallel. You can think of it like farmers planting seeds for the next harvest, even while the current one is still being gathered. While we are still optimizing 5G's potential in applications like smart factories, automated logistics, and remote surgery, we are simultaneously exploring how 6G could connect not just devices, but intelligence itself. 6G aims to merge communication and computation so that networks become context-aware, capable of predicting and adapting to human needs in real time. This means that by the time 2030 arrives, we will not simply have faster phones. We will have a new digital environment where sensing, AI, and connectivity operate as one ecosystem. When we connect all these ideas, we see the timeline of wireless evolution as a continuous journey of innovation. 5G began its global rollout around 2020, and by 2025, it will be deeply embedded in both consumer and industrial life. At the same time, 6G research is gaining momentum, with the first real-world tests already underway and commercial readiness expected around 2030. These developments highlight one essential truth about communication technology. It never stops evolving. Each generation builds upon the lessons of the previous one, addressing new demands that emerge as society becomes more digital and interconnected. To conclude today's discussion, 5G represents the present, a technology that is actively shaping industries and daily life through high-speed, reliable connectivity. 6G represents the future, a vision of networks that are faster, smarter, and deeply integrated with artificial intelligence. The journey from 5G to 6G is not just about technological progress, but about human progress, enabling a world where communication becomes as natural and seamless as thought itself. As future communication engineers, your role will be to bridge these two worlds, optimizing what exists while creating. So, as we move toward 2030, remember that the story of wireless evolution is still being written, and you have the opportunity to be one of its authors. Imagine waking up in a future where your doctor performs a health check on you from miles away, your car drives you to work safely while you relax, and your favorite concert feels like it's happening right in your living room. All of these futuristic scenes are not from science fiction, but are real possibilities powered by 5G and 6G technologies. So today, let's explore the question, where can 5G and 6G be used? The main idea of this slide is that these networks will revolutionize industries such as healthcare, manufacturing, transportation, and entertainment by enabling faster, smarter, and more reliable connectivity. They are not just about improving communication, but about transforming how our world functions across every major sector of society. Let's walk through how these technologies are changing lives in very different but equally powerful ways. Let's begin with healthcare and manufacturing. In healthcare, imagine a surgeon operating on a patient located in another city through a robotic arm. The precision of that robot depends entirely on real-time data transfer. Even a delay of a few milliseconds could be dangerous. This is where 5G makes the impossible possible. Its ultra-reliable low-latency communication allows surgical tools to respond instantly, as if the doctor were right there. You can think of 5G as the nervous system of a human body. When you touch something hot, your reflex happens almost instantly. 5 enables networks to react with the same speed and reliability, which can literally save lives. In manufacturing, 5G turns traditional factories into smart factories. Robots, sensors, and machines all communicate seamlessly, adjusting production lines automatically when an error is detected. It's like conducting an orchestra, where every instrument stays perfectly in sync because the conductor, in this case, the network, ensures flawless coordination. With 6G, these systems will go even further by integrating real-time AI decision-making, predicting problems before they even occur. Now let's move to transportation and entertainment. Imagine a city filled with autonomous cars, all communicating constantly with each other and with traffic lights, pedestrians, and buildings. To function safely, they need instant updates about road conditions, speed, and obstacles. 5G enables this level of communication by supporting ultra-low latency and high reliability. It's like having cars that can read each other's minds, coordinating every movement to prevent accident. The result is not just convenience, but a massive improvement in safety and traffic efficiency. Meanwhile, in the world of entertainment, 5G opens up experiences that were previously impossible. Virtual reality and augmented reality depend on massive data transfers in real time. For example, when you wear a VR headset, even a tiny delay can make the experience uncomfortable or unrealistic. 5G's high speed and stability solve that problem, allowing users to experience concerts, sports, and games as if they were happening right in front of them. With 6G, this will evolve into fully immersive environments that blend the digital and physical worlds seamlessly. Transitioning from these applications, let's consider the broader impact on industrial automation and infrastructure. 5G acts as the backbone for smart cities, where systems like energy grids, waste management, and public transportation all work intelligently together. Imagine a city that senses its own needs, rerouting traffic automatically when congestion occurs, or adjusting energy distribution during peak hours. This type of coordination requires massive machine-type communication, something that 5G handles efficiently. In industrial settings, 6G will introduce even more advanced control through edge computing, allowing factories or utilities to make split-second decisions locally without waiting for instructions from distant servers. You can think of this as giving every machine its own brain, capable of processing data and acting immediately. This leads to greater efficiency, reduced downtime, and enhanced sustainability. The shift from human-monitored systems to autonomous, data-driven ecosystems will redefine productivity and resource management on a global scale. Finally, let's talk about how 5G and 6G will transform education and public services, areas that directly affect people's daily lives. During the pandemic, we saw how critical reliable internet connectivity became for remote learning and communication. However, 4G networks often struggled with bandwidth and consistency, especially in crowded areas. 5G solves this by providing higher capacity and more stable connections, allowing virtual classrooms to run smoothly even with thousands of participants. Beyond that, future 6G networks could enable immersive learning experiences using holograms or interactive 3D simulations, where students can explore scientific concepts or historical events as if they were physically present. In public services, governments can use these networks for smart surveillance, emergency response coordination, and disaster management. For example, 5G drones could deliver medical supplies to isolated regions, while 6G might integrate environmental sensing systems to detect earthquakes or floods before they happen. Just as electricity once transformed every aspect of life, 5G and 6G will become the invisible infrastructure that powers the intelligence of modern civilization. When we connect all these examples, a clear picture emerges. 5G and 6G are not just communication upgrades, but foundational technologies that will reshape every industry. Healthcare becomes faster and safer. Manufacturing becomes smarter and more automated. Transportation becomes more efficient and secure, and entertainment becomes more immersive and realistic. On top of that, education, public safety, and city management will reach levels of efficiency we could only dream of before. These networks represent a shift from connecting people to connecting everything, everywhere, all the time. To conclude today's discussion, the true value of 5G and 6G lies not in their speed alone, but in their ability to enable innovation across all areas of human activity. They are the nervous system of a new digital society, carrying information instantly and intelligently where it is needed most. As future engineers, your role will be to design and optimize these systems, ensuring that this technology continues to serve humanity in meaningful and responsible ways. So, the next time you hear about 5G or 6G, don't just think of faster internet. Think of the hospitals that save lives, the cars that prevent accidents, and the cities that learn and adapt, all connected by the invisible threads of wireless communication that you will one day help to build. Imagine standing in a concert hall where thousands of musicians are playing together. Each instrument produces a unique sound, yet everything blends into harmony because they follow the same rhythm and frequency structure. This is similar to how wireless networks work. Every smartphone, sensor, and device sends signals using specific frequencies, and the key to faster, more reliable communication lies in how we organize and manage those frequencies. Today, we are going to explore how 5G and 6G work. The main idea of this slide is that 5G and 6G use advanced radio wave technologies and intelligent network architectures to transmit data faster, handle far more devices, and support real-time communication. These networks are not just faster versions of the old ones. They are fundamentally smarter, built to sense, adapt, and optimize themselves automatically. Let us begin with high-frequency technology. In 5G, we use what are called millimeter waves, which operate at frequencies much higher than those used by 4G. You can imagine frequency as a road. The higher the frequency, the wider and smoother the road becomes, allowing more data cars to travel at once. 4G used frequencies around a few gigahertz, while 5G moves up to tens of gigahertz, opening up new lanes for massive data traffic. This is why 5G can deliver extremely high speeds, enough for streaming high-definition videos, supporting autonomous vehicles, and enabling real-time artificial intelligence. However, these higher frequencies have a trade-off. They cannot travel as far and are more easily blocked by buildings or even rain. That is where the network design becomes critical. As for 6G, it will likely move into the terahertz range, an even higher frequency band. You can think of terahertz as a superhighway built in the sky, carrying enormous amounts of information almost instantly. With that, we can expect data rates up to 1 terabit per second in latency, so low that communication feels instantaneous. Now that we understand the role of frequency, let us talk about network structure, particularly the small cell network layout. Traditional networks use large base stations that covered wide areas, much like having one lighthouse to guide an entire coastline. But as demand for data increased, that model became inefficient. In 5G, we shift to small cells, meaning we place many base stations closer together, each covering a smaller area, but providing stronger and faster connection. This approach is like replacing one giant lighthouse with a network of streetlights, each bright enough to illuminate its own corner. The result is lower latency and higher reliability, especially in crowded urban environments. Because these small cells are distributed densely, they can handle more users and ensure stable performance even during peak hours. In 6G, these cells will work together with intelligent algorithms that adjust power, bandwidth, and routing automatically to maintain perfect balance across the network. Next, let's explore how intelligent management enhances network performance. In earlier generations, network parameters were mostly fixed, set to handle the worst-case scenario. It's like driving a car with one fixed gear no matter the road condition. Sometimes it's too slow, other times it wastes energy. 5G starts changing this by using software-defined networks and machine learning to optimize performance in real time. The system can detect when certain areas are overloaded and automatically allocate more bandwidth there while reducing power in areas with fewer users. In 6G, this concept will evolve into full autonomy. Artificial intelligence will be embedded directly into the network core, allowing it to predict demand before congestion happens. Imagine a smart traffic system that reroutes cars before a traffic jam forms. That is exactly how 6G networks will behave. They will learn user patterns, sense environmental conditions, and adapt dynamically, achieving what we call zero-touch management, meaning the network runs itself efficiently without constant human intervention. Another key factor in how these systems work is the integration of computation with computation. In 4G and earlier generations, the network's job was simply to transfer data from point A to point B. In 5G and especially 6G, communication and computation merge. You can think of it as combining a road network with a series of mini data centers along the way. When a device sends information, the network can process it locally rather than sending it all the way to a distant cloud. This technique, known as edge computing, dramatically reduces latency and energy consumption. For example, if an autonomous car detects a pedestrian, it does not have time to wait for a response from a faraway server. Instead, the network processes that information right at the edge, allowing the car to react instantly. In 6G, edge computing will be tightly integrated with AI to enable real-time learning and decision-making across millions of connected devices. It will feel as if the entire network has a collective brain that processes and responds within microseconds. Now, when we combine high-frequency transmission, small cell networks, intelligent management, and integrated computing, we begin to see the full picture of how 5G and 6G operate. Each layer supports the next, forming a system that is not only faster, but fundamentally more adaptive and self-aware. The diagram on the slide illustrates how 5G's protocol stack relies on static parameters, while 6G's architecture integrates artificial intelligence directly into its control plane. This means that in 6G, the network no longer just follows commands. It learns and makes decisions on its own to optimize performance continuously. To summarize, 5G and 6G work by combining breakthroughs in radio frequency engineering, network topology, and artificial intelligence. 5G uses millimeter wave technology and dense small cell layouts to deliver ultra-fast, low-latency connections. It introduces intelligent network management that can respond to changing conditions dynamically. 6G will take all of this further, using terahertz frequencies, AI-driven optimization, and edge computing to achieve communication speeds and reliability far beyond what we have today. In simple terms, 5G gives our networks muscles, while 6G gives them a brain. As future communication engineers, understanding how these systems operate beneath the surface will allow you to design networks that are not only powerful, but also intelligent, shaping the connected world of the future. Imagine waking up in the morning and your smart home already knows what you need. The lights turn on gently, the air conditioner adjusts to your preferred temperature, and your watch quietly updates you on your health statistics overnight. Outside, traffic is flowing smoothly because every vehicle is communicating in real time, preventing congestion before it even begins. What makes all of this possible? That is the question behind today's topic. How will 5G and 6G change life? The key message of this slide is that 5G and 6G technologies will dramatically transform our daily lives, industries, and society through faster connectivity, smarter cities, and artificial intelligence-driven solutions. These advances are not simply about speed. They represent a shift toward an intelligent, responsive, and connected world where digital systems integrate seamlessly with human life. Let's start with the first aspect: improvements in everyday life. Think about the frustration of waiting for a video to buffer or a game to load. With 5G and later 6G, that delay practically disappears. It is like replacing a narrow water pipe with a massive river where data flows smoothly and endlessly. Streaming ultra-high definition video or exploring virtual reality environments will feel instantaneous, creating truly experiences. Imagine putting on a headset and attending a concert or a lecture that looks and sounds perfectly real, without any lag or distortion. That kind of real-time interactivity changes how we learn, work, and entertain ourselves. But the benefits go beyond leisure. Low latency means our communication becomes as natural as speaking face-to-face, regardless of distance. 6G will push this even further, enabling tactile communication, where not only sight and sound, but even touch can be transmitted digitally, allowing humans to experience presence across space. Now let's discuss wearable technology and health monitoring. In a sense, 5G and 6G will turn our bodies into connected networks. Wearable devices from smartwatches to medical implants will collect and share data continuously with healthcare providers. You can think of it like having a digital twin of yourself, an always-on companion that watches over your well-being. For example, a person with a heart condition could have sensors that detect irregular rhythms and alert doctors instantly. This constant flow of information allows early detection and intervention, saving lives. At home, smart devices will communicate through the network to maintain comfort and energy efficiency automatically. When combined with 6G's potential for ubiquitous connectivity, every object in our environment becomes part of a larger intelligent system. The home evolves from being a passive space into an active participant in daily life, one that learns your routines, predicts your needs, and responds to them instantly. Moving from individual experiences to broader social transformation, let us look at smart cities. A smart city is like a living organism whose nervous system is built from networks of sensors and communication links. With 5G, cities can collect and analyze real-time data from traffic, energy grids, and public services. This means traffic lights adjust dynamically to reduce congestion. Waste collection happens only when bins are full, and emergency response teams are guided by real-time situational data. Imagine if the entire city could think and react like a single intelligent entity. That is what networked communication enables. The use of 6G will amplify this intelligence by integrating AI directly into city management. For example, energy systems could automatically balance supply and demand, reducing carbon emissions without human intervention. This is like giving cities a brain that constantly learns from its environment to optimize performance. Smart cities will not just be efficient, but also sustainable and safe, supporting a higher quality of life for everyone. Now let us turn to how industries and factories are changing under this transformation. In the past, industrial automation was limited by latency and the need for wired systems. 5G eliminates that limitation, allowing wireless control of robots, drones, and complex machinery with millisecond precision. Think of it like replacing a network of tangled wires with an invisible, intelligent nervous system that connects every machine. This makes factories more flexible and responsive. Production lines can adapt in real time to changing demand, and predictive maintenance systems can detect faults before they happen. With 6G, AI-driven automation will reach an even higher level of sophistication. Machines will communicate directly with each other, making autonomous decisions to improve efficiency. It is like having a team of workers who not only follow instructions, but also think, plan, and cooperate on their own. This transformation does not just increase productivity, It reduces risks for human workers and enables industries to achieve precision and sustainability at a scale never seen before. Between these examples, you can see a common thread. Whether it is your smartphone, your car, your city, or an industrial plant, everything is becoming part of an intelligent, interconnected ecosystem. The transition from 5G to 6G represents more than technological progress. It is the evolution of our relationship with machines and information. The world will no longer be divided between the digital and the physical. Instead, they will merge into a single hybrid reality, where decisions, responses, and interactions happen simultaneously across both spaces. To summarize today's discussion, 5G and 6G are set to redefine the way we live and work. In everyday life, they bring instant connectivity, immersive experiences, and intelligent personal devices that enhance comfort and health. In society, they enable smart cities that think for themselves, managing resources efficiently and improving sustainability. In industry, they create autonomous systems that boost productivity and safety. Together, these technologies will make the invisible threads of communication the foundation of modern civilization. The real question for us as engineers is not only how fast these systems can be built, but how wisely they can be used. The next generation of communication is not about connecting more devices. It is about connecting life itself, making technology an extension of human intelligence. And as future engineers, you will be the ones to ensure that this connection leads us toward a smarter, safer, and more human world. Imagine this. You buy a new 5G smartphone, excited to experience the lightning-fast speed everyone has been talking about. You open a video app, and yes, it loads quickly, but then you realize your 4G phone did almost the same thing. You might even ask yourself, where's the difference? Why don't I feel the power of 5G in my everyday life? That question leads us perfectly to today's topic. Why is 5G adoption slow? The key message of this slide is that 5G was originally designed for very specific applications such as IoT, autonomous systems, and ultra-reliable, low-latency communication, not just for regular phone use. Because many of these advanced technologies are not yet widely implemented, 5G's full potential remains largely untapped. Let's look deeper into why this is happening and what it tells us about the relationship between technology and society. First, we need to understand that 5G vision was built around IoT, which stands for Artificial Intelligence plus Internet of Things. Think of IoT as an ecosystem where billions of devices, from sensors to machines, work together intelligently. For example, in a smart factory, robots communicate with each other in milliseconds to coordinate production. In healthcare, patient monitors send real-time data to doctors who can respond instantly. These are the kinds of applications that truly need 5G, low latency and massive connectivity. But here is the problem. Most industries have not yet reached that level of digital transformation. It's like building a superhighway before cars are invented. The infrastructure is there, but the traffic is missing. Many companies are still using traditional systems or limited Wi-Fi networks, and deploying IoT at scale requires huge investment, new regulations, and workforce training. So while 5G technology is ready, the ecosystem that depends on it is still catching up. This delay in IoT adoption directly slows down 5G's growth. The second reason for slow adoption is that most everyday users simply do not need the extreme speed or low latency that 5G offered. To put it simply, 5G is overqualified for how we currently use our phones. Think about it like this. If you only drive around a small town, owning a Formula One race car might sound impressive, but you will never get to use its full power because the roads and speed limits are not designed for it. The same goes for 5G. For basic tasks like watching videos, scrolling social media, or messaging friends, 4G is already fast enough. In fact, the difference between downloading a movie in 10 seconds versus 2 seconds doesn't really change the user experience. This is why many consumers do not feel motivated to pay more for 5G plans or upgrade their devices. Telecom companies built networks for future demands, but the majority of people still live in the present where those demands don't yet exist. Now let us explore the third challenge, the cost and complexity of infrastructure. Unlike 4G, which relied on large cell towers, 5G uses a dense network of small cells placed closer together. It is similar to replacing a few tall water towers with thousands of smaller pumps distributed around the city. This design allows for higher frequency signals that provide faster data but travel shorter distances. However, installing so many small cells requires enormous investment, especially in urban areas where space, permits, and maintenance costs are high. For developing regions, this becomes an even greater barrier because the return on investment is not immediate. Operators must balance between upgrading existing 4G systems and deploying 5G, often choosing a hybrid model known as non-standalone 5G, which still depends partly on 4G infrastructure. This slows down the rollout of full standalone 5G networks that can deliver the real benefits of ultra-low latency and AI integration. The result is a patchwork of network quality and coverage that makes it difficult for users to experience consistent 5G performance. The fourth factor involves perception and awareness. Many people still see 5G as just another step in faster internet, rather than a technological shift that enables entirely new possibilities. Imagine giving someone a smartphone before the invention of mobile apps. Without understanding its potential, they would treat it like an ordinary phone. Similarly, 5G's power lies in what it can enable, not just in raw speed. It is the foundation for smart transportation, remote surgery, virtual reality collaboration, and industrial automation. But these concepts are abstract to most consumers, and industries have yet to provide widely accessible applications that make these benefits tangible. This creates a communication gap between what 5G can do and what people actually experience. As engineers, we must remember that adoption depends not only on technical readiness, but also on social understanding and usability. Technology only becomes successful when it fits naturally into daily life. When we connect all these points, we begin to see the bigger picture. The slow adoption of 5G is not a failure of engineering, but a reflection of timing and context. The technology was designed ahead of its time, anticipating a world that is still under construction. IoT ecosystems are still developing. Everyday users do not yet need ultra-fast networks. The infrastructure is expensive and complex, and public understanding of 5G's true potential remains limited. It's like a symphony where the instruments are ready, but the orchestra has not yet started playing in harmony. To conclude today's discussion, 5G's slow adoption teaches us an important lesson about the rhythm of innovation. Engineering progress often outpaces real-world demand. 5G was built to serve a future of connected intelligence, but that future is still forming. As future communication engineers, your challenge will not only be to design faster systems, but to ensure they are meaningful, accessible, and integrated into society. The success of 5G and eventually 6G will depend on how well we align technology with human needs. So the next time someone asks why 5G feels no different from 4G, you can tell them, the network is ready, we are just waiting for the world to catch up. Imagine two runners starting a race on the same track. One represents 4G, the other 5G. When the race begins, 4G quickly sprints ahead, gaining millions of users within a year, while 5G lags behind, moving more slowly despite being younger, faster, and strong. You might wonder, how could the newer, more advanced technology fall behind? This is what we are going to explore today in our topic titled 4G versus 5G Adoption in 1 year. The key idea is that 4G spread much faster than 5G in its first year, because 5G faces higher, costs more complex infrastructure requirements, and different usage scenarios that make large-scale expansion more difficult. Let's unpack why this happened and what it teaches us about how technology evolves not only through engineering progress, but also through economics and practicality. Let's start with the data. In its first year, 4G reached more than 6 million users with a penetration rate of nearly 28%. In contrast, 5G reached only about 2.7 million users, or around 11% penetration. That is less than half the adoption speed. At first glance, this seems surprising because 5G promises far higher speeds, lower latency, and greater efficiency. But to understand why adoption slowed, we have to look at the environment in which 5G was launched. When 4G arrived, it was a clear upgrade from 3G, enabling streaming, social media, and the mobile internet revolution. Everyone could immediately feel the improvement. 5G, however, was designed for more advanced applications such as IoT, autonomous vehicles, and industrial automation, which are still developing. So the race is not about who is faster in theory, but who fits better into people's everyday needs at the time. One of the biggest obstacles to 5G's rapid expansion is the high cost of spectrum licensing. Governments allocate frequency bands for telecom companies through auctions, and these licenses often cost billions of dollars. Think of spectrum as real estate in the air. The higher the frequency and the more bandwidth you want, the more expensive that property becomes. Telecom companies have to compete fiercely to secure enough spectrum for 5G services, and this bidding war consumes enormous financial resources. It's like buying a luxurious plot of land before you even have the money to build a house on it. As a result, operators often have less capital left for actual network deployment. Instead of quickly building base stations and expanding coverage, they must move carefully, balancing financial risk. This is one reason why 4G could expand faster. Its spectrum costs were lower, and its target applications were already proven and profitable. Another critical factor is the cost and complexity of infrastructure. 5G operates at higher frequencies, which means its signals have shorter wavelengths and cannot travel as far as 4G signal. To maintain reliable coverage, 5G requires a denser network of base stations placed closer together. You can imagine 4G as a system of lighthouses, each one casting its light over a wide area, while 5G is more like a series of street lamps, each covering only a small space but providing clearer, brighter illumination. Building this dense network takes both time and money. Each new station requires land, permits, power supply, and maintenance. In urban areas, finding suitable installation points can be challenging, and in rural areas, it becomes uneconomical because there are fewer users to justify the cost. This means 5G rollouts often start in major cities and expand gradually, whereas 4G could spread nationwide much more easily. There is also a difference in user perception and market ready. When 4G launched, consumers were eager for faster mobile internet because they could instantly use it for streaming and browsing. The benefits were visible and relatable. But with 5G, most users do not experience a dramatic improvement in daily tasks like texting or watching videos because 4G already meets those needs. It's like upgrading from a sports car that drives 200 kilometers per hour to one that drives 400. But you are still stuck in city traffic where you can only go 60. The infrastructure and applications that would showcase 5G's true potential, such as autonomous driving and smart factories, are still in early development. Without compelling new use cases, many users see little reason to pay extra for 5G plans. This creates a slower adoption cycle. Fewer users mean lower revenue for telecom companies, which in turn limits further investment in expansion. Now let's connect these pieces together. 4G's rapid adoption was driven by a perfect storm of factors: affordable spectrum, straightforward infrastructure, and clear consumer demand. It arrived at a time when the world was ready for mobile data and video streaming, and it filled that gap instantly. In contrast, 5G was built as a foundation for future technologies rather than a direct consumer upgrade. It's like designing a spaceport before people are ready to travel to Mars. The technology is impressive, but it takes time for society to catch up. Governments, industries, and consumers must all align before full adoption becomes realistic. Until then, 5G's rollout remains slower and more uneven than 4G's early growth. To conclude today's discussion, 5G's slower adoption is not a sign of weakness, but a reflection of complexity. The high cost of spectrum licensing drains investment budgets. The dense infrastructure requires more resources and planning. And current user needs have not yet reached the point where 5G capabilities become essential. 4G grew quickly because it solved immediate problems people already had, while 5G is preparing for challenges that are still emerging. As communication engineers, we must remember that technological innovation is only part of the equation. Economics, policy, and timing play equally important roles in determining how fast new systems are embraced. So when you hear that 4G outpaced 5G in its first year, think of it not as a failure but as an evolution. 5G is not sprinting to win a short race. It is building the foundation for the marathon of the future, where intelligent connectivity will transform every corner of modern life. Imagine you are assembling a complex machine, like a drone. You buy a camera from one company, a motor from another, and a controller from a third. When you put them together, they fit perfectly and the drone flies smoothly. Now imagine the opposite scenario, where every component is locked into one manufacturer's proprietary system. You are forced to buy everything from the same vendor, often at higher prices and with limited customization. Which system would you prefer? Most engineers would choose the open one, because it allows flexibility, innovation, and cost efficiency. That same principle lies at the heart of today's topic, why open source and open architecture are key for 5G. The main idea is that open source projects and open network architectures make 5G more affordable, more adaptable, and more innovative by allowing telecom operators, developers, and researchers to collaborate within a shared standardized ecosystem. Let's begin with the first major concept: lower cost and more choices. Traditional telecom systems relied heavily on closed architectures, meaning each part of the network, from antennas to software, had to come from a single vendor. It is like being locked into one brand of car parts. If your brake system fails, you can only replace it with that manufacturer's expensive components. Open source and open architecture changed this by creating standardized interfaces that allow operators to mix and match components from different vendors. Organizations like the O-RAN Alliance lead this effort by defining open interfaces for radio access networks, enabling interoperability. This approach not only reduces costs, but also increases competition among suppliers, driving innovation and better service quality. It is like having a modular kitchen where you can replace or upgrade any part without rebuilding the whole room. The freedom to choose lowers dependency on monopolized systems and ensures that smaller companies can enter the market, making the entire ecosystem more dynamic and sustainable. The second key point is faster innovation and collaboration. In closed systems, innovation moves slowly because only one company controls the design and improvement cycle. But when the architecture is open, many minds can contribute simultaneously. Think of it like a public library where anyone can add new books or improve existing ones, rather than a private collection locked behind a door. With open source projects such as ONAP or Open Network Automation Platform, researchers, telecom companies, and software developers around the world work together to develop and refine network automation. This collective approach speeds up the creation of new features and reduces the time from concept to deployment. When someone finds a solution to a network optimization problem, they can share it immediately, and others can build upon it. In engineering terms, it turns a linear innovation process into a parallel one, multiplying progress by the number of active contributors. This is especially important for 5G, where technologies like network slicing, edge computing, and AI-based management require constant experimentation and rapid adaptation. Moving on, let's discuss how open source fosters global standards and interoperability. One of the biggest challenges in communication systems is ensuring that equipment and software from different vendors can work seamlessly together. Without standardization, networks become fragmented, leading to inefficiency and incompatibility. Open architectures promote common frameworks that everyone can follow, similar to how USB became the universal connector for electronic devices. Once a global standard is established, developers can focus on improving performance rather than reinventing basic function. The O-RAN specifications, for example, define how base stations communicate with each other regardless of the manufacturer. This creates an environment where innovation focuses on quality, not exclusivity. It is like a shared musical score that allows different musicians to play in harmony, even if they use different instruments. When everyone follows the same notes, the result is coherent and scalable, not chaotic and disjointed. Now let's look at the economic and social impact of open collaboration. By reducing costs and encouraging shared innovation, open architectures democratize access to technology. Smaller telecom companies, universities, and startups can participate in 5G development without needing massive budgets. This inclusiveness leads to diverse perspectives and more creative solutions. Imagine a neighborhood garden where everyone contributes their own seeds and ideas. The variety makes the ecosystem richer and more resilient. Similarly, open systems encourage cross-border partnerships and accelerate technology transfer between academia and industry. Governments also benefit because open networks reduce dependency on foreign vendors, enhancing national security and technological independence. Moreover, as the 5G ecosystem matures, the lessons learned from open collaboration will pave the way for 6G, where artificial intelligence and automation will play even larger role. The foundations we build today will shape how efficiently and ethically future communication systems evolve. All these factors, cost efficiency, rapid innovation, global standards, and inclusiveness, combine to make open source and open architecture indispensable for 5G success. Closed systems may have worked in earlier generations, but 5G's complexity requires a broader, more flexible approach. The networks of the future must be as dynamic as the societies they serve, capable of adapting quickly to new demands and technology. Just as open ecosystems in nature thrive through diversity and cooperation, open communication networks thrive through shared knowledge and collaboration. To summarize, open source and open architecture are not just technical trends. They represent a fundamental shift in how we build and manage communication systems. They allow telecom operators to lower costs by choosing from multiple vendors, accelerate innovation through collaboration, and ensure compatibility through global standards. They also empower more participants to contribute, transforming the 5G ecosystem into a living, evolving network of ideas and solutions. As future engineers, you should recognize that the most powerful designs are not those locked behind walls, but those built in open communities where knowledge flows freely. The success of 5G, and even more so 6G, will depend on our willingness to share, collaborate, and innovate together. In the world of communication, openness is not just a philosophy, it is the key to progress. Imagine you walk into a restaurant where every dish on the menu is made by a single chef. The food might be good, but you have no choice in flavor or price. And if the chef leaves, the restaurant shuts down. Now, imagine a food court instead, where many chefs work side by side, each offering their own specialty, all sharing the same kitchen space and standard. You can mix and match freely, finding the best balance between quality and cost. That second scenario perfectly illustrates the spirit behind O-RAN, or Open Radio Access Network. Today's topic is why O-RAN is becoming a consensus. The key idea of this slide is that O-RAN is widely accepted because it promotes open architecture and open source collaboration, balancing business interests for both telecom operators and vendors, while encouraging innovation, flexibility, and cost efficiency across the 5G ecosystem. Let us start by understanding what O-RAN really represents. In traditional telecom systems, Network equipment was largely closed and proprietary. A single vendor provided the hardware, software, and interfaces, which meant operators were locked into one supplier. This model worked for decades, but as 5G networks became more complex and data-intensive, it started to limit innovation and increase costs. O-RAN challenges that by introducing openness at every layer of the radio network. It standardizes how components communicate, allowing equipment from different vendors to work together seamlessly. You can think of it as turning the telecom network into a Lego set where pieces from different brands can still fit perfectly. This flexibility gives operators more control and vendors more opportunities, making it a win-win model that the industry increasingly embraces. Now let's move to the first major point: clear objectives for buyers and sellers. Telecom operators, who are essentially the buyers, have one primary goal: to deliver reliable and fast connectivity at the lowest possible cost. They want systems that are flexible, scalable, and vendor-neutral. O-RAN meets these goals by breaking down the network into modular components that can be sourced competitively. Instead of buying a full system from one supplier, operators can now choose the best parts from multiple vendors. Vendors, on the other hand, also benefit because open standards create a broader market. In the past, they had to develop custom solutions for each operator, which limited their reach. With O-RAN, a standardized interface means a product built for one network can be sold globally. Imagine if every smartphone charger used a different plug. It would be a nightmare. O-RAN is like introducing the USB standard to telecom, ensuring compatibility for everyone. This alignment of goals between buyers and sellers is one of the key reasons O-RAN is gaining such wide consensus. Next, let's explore the idea of mutual benefits driving adoption. When the telecom market was dominated by closed systems, competition was limited and innovation moved slowly. O-RAN changes that dynamic by opening the field to more participants. It's like turning a private research lab into a public innovation center where scientists from everywhere can collaborate. By reducing reliance on proprietary hardware and software, O-RAN lowers entry barriers for new players, including startups and research institutions. This not only drives down costs, but also accelerates technological advancement. Fair competition means better solutions and more rapid improvement. For example, when multiple vendors compete to provide the best radio unit or software algorithm, each has an incentive to innovate faster. At the same time, operators can mix and match the best performing components, creating a self-improving ecosystem. This mutual benefit fuels adoption because both sides see tangible advantages. Operators save money, while vendors expand their market share. Let's also consider how O-RAN enhances scalability and adaptability in the long term. In traditional networks, expanding coverage or upgrading systems often required replacing entire sections of hardware, which was costly and inefficient. O-RAN's modular and software-driven design makes upgrades much simpler. It's like updating an app on your phone rather than buying a new device every time. Operators can deploy new software functions remotely and integrate AI-based management systems that automatically optimize network performance. This flexibility is especially important as 5G evolves towards 6G, where networks will need to handle massive data volumes and dynamic real-time applications. Because O-RAN is built on open standards, it can easily adapt to new technologies without requiring a complete rebuild. This future-proofing aspect gives both industry players and governments confidence that investing in O-RAN will pay off over time. Moreover, O-RAN's collaborative model has created a powerful global movement involving alliances, organizations, and open-source projects. The O-RAN Alliance works closely with 3GAP, GSMA, and other standardization bodies to ensure consistency and interoperability. Meanwhile, open-source platforms like LF Networking and OpenChain provide shared resources where companies can test, validate, and refine O-RAN implementation. It's like a worldwide workshop where engineers from different backgrounds come together to solve shared problems. This global cooperation transforms O-RAN from just a technical framework into a unifying vision for the entire telecom industry. Instead of competing behind closed doors, companies are now co-developing solutions in open environments, which increases trust, transparency, and speed of innovation. As we bring these ideas together, the consensus around O-RAN becomes clear. It aligns the interests of both telecom operators and vendors through transparent objectives, provides mutual economic and technological benefits, and fosters a collaborative ecosystem that accelerates innovation. The open model replaces exclusivity with inclusivity, ensuring that the 5G and future 6G networks are not just faster but smarter, more affordable, and more adaptable. O-RAN represents a fundamental shift from competition to cooperation, showing that in the modern world, openness is not a weakness, it is a strength. To conclude, O-RAN is becoming the new consensus because it successfully balances technology, economics, and collaboration. For operators, it means lower costs and greater control. For vendors, it opens doors to a global standardized market. For researchers and innovators, it provides a platform for experimentation and shared progress. The telecom industry has realized that the challenges of next-generation networks cannot be solved by working alone. They require collective intelligence, shared standards, and open communication, principles that O-RAN embodies. As future engineers, you will inherit this open ecosystem, and your ability to collaborate across disciplines and industries will define how well it thrives. O-RAN is not just a new architecture. It is a new mindset that redefines how we build the connected world of tomorrow. Imagine you are standing at a theme park watching people line up for a brand new roller coaster. At first, there's excitement and curiosity. Everyone wants to be the first to try it. But after a few rides, some discover that it is not as thrilling as expected, and the long lines start to disappear. Later, the ride gets improved, safety increases, and the crowd returns steadily. This pattern of excitement, disappointment, and maturity is very similar to how technology evolves over time. Today, our topic is how to choose tech careers using the hype cycle. The key idea is that by understanding where a technology is in its hype cycle, you can make smarter career decisions, choosing fields that will reach maturity or peak opportunity when you graduate. It's about being in the right place at the right time, not just following trends blindly. Let's begin by understanding what the hype cycle actually is. The hype cycle, proposed by Gartner, describes how technologies develop through 5 distinct stages. The first stage is the innovation trigger, where a new idea or technology first appears. It is like the first announcement of that roller coaster. Everyone is curious, but few know how it really works. Then comes the peak of inflated expectations, when people believe the technology can solve every problem imaginable. This is when media, hype, and investor interest are at their highest. After that, we hit the trough of disillusionment, where reality sets in and the technology fails to meet those high expectations. Some projects collapse and funding slows down. However, the survivors move to the slope of enlightenment, when practical use cases start emerging and engineers refine the design. Finally, the technology enters the plateau of productivity, where it becomes stable, widely adopted, and generates real value. Understanding these 5 stages is like reading the pulse of innovation. It allows you to predict which technologies are about to rise and which are falling into decline. Now let's connect this to your career choices. As engineers, choosing which field to specialize in is one of the most important decisions you will make. Timing your choice according to the hype cycle can significantly influence your opportunities and job stability. Think of it like investing in stock. If you buy when prices are at their peak, you risk losing money when the hype fades. But if you invest when the market has stabilized and long-term growth is clear, you build sustainable wealth. Similarly, if you enter a technology too early during its hype stage, you might find that the excitement fades before the market matures. On the other hand, if you join a field that is climbing the slope of enlightenment or entering the plateau of productivity, you can ride the wave of real-world adoption. For example, when cloud computing first emerged, it went through an intense hype phase. But those who entered during its refinement years built solid careers as the technology matured and became essential infrastructure. To illustrate this further, let's apply it to current technologies like 5G, artificial intelligence, and quantum computing. 5G is now moving past its early hype stage and entering the phase of real industrial implementation. This makes it an excellent field for students who will graduate in a few years, as demand for skilled engineers in network optimization, IoT, and edge computing continues to rise. Artificial intelligence, meanwhile, is somewhere between the peak of expectations and the slope of enlightenment. There is still a lot of exaggerated talk about AI replacing human creativity, but at the same time, we are starting to see meaningful, practical applications in healthcare, transportation, and education. Careers related to AI ethics, model optimization, or human-AI collaboration will be especially valuable as the field matures. Quantum computing, however, is still near the innovation trigger stage. It's fascinating and full of potential, but its commercial applications are not yet stable. Entering it now requires a long-term vision and tolerance for uncertainty. Understanding where each technology stands helps you align your education and career goals strategically. Another aspect to consider is how the hype cycle interacts with industry trends. For instance, technologies like augmented reality and virtual reality once sat at the peak of inflated expectations, but are now climbing the slope again as hardware improves and enterprise use cases grow. Those who left the field early missed the resurgence, while those who stayed to refine practical solutions are now leading innovation. The lesson here is not to chase hype, but to recognize the value of persistence and timing. Like in signal processing, where you must filter out noise to detect the true signal, you need to filter out hype to see genuine technological progress. When you can distinguish between temporary excitement and long-term potential, you position yourself ahead of the crowd. Let's also talk about how you can practically use the hype cycle when planning your education. As students, you have the advantage of time. Suppose you identify a technology currently in the early hype phase. By the time you graduate, it may have reached maturity, giving you a head start in a growing job market. For example, research areas like 6G, green communication systems, or AI-driven networking are still emerging, but they will likely become mainstream within the next 5 to 7 years. This means students who start preparing now will be ready when industry demand peaks. It's like planting a tree. You need to start early to enjoy the shade later. Now, an important reminder, not every technology follows the same timeline through the hype cycle. Some move rapidly, like smartphone apps, while others, like telecommunication standards, evolve over decades. Therefore, your career planning should balance both short-term employability and long-term growth. Choosing a field that combines stable technologies with emerging ones can give you flexibility. For instance, working on 5G implementation now, while exploring 6G research, prepares you for both immediate opportunities and future innovation. To summarize today's discussion, the hype cycle is a powerful tool for career strategy. By understanding its 5 stages, innovation trigger, peak of inflated expectations, trough of disillusionment, slope of enlightenment, and plateau of productivity, you can interpret where technologies stand and how they will evolve. Timing your career choice means selecting a field that will reach maturity just as you enter the job market, ensuring strong demand for your skills. The key takeaway is that successful engineers are not those who chase trends, but those who anticipate where value will emerge and position themselves accordingly. In technology, just like in life, the goal is not to run the fastest, but to run in the right direction at the right time. So as you plan your future, remember that the hype cycle is not just a graph, it is a map that can guide your journey through the ever-changing landscape of innovation. Imagine you are standing in front of a buffet table with hundreds of dishes. Some are surrounded by long lines of people, others are untouched but smell amazing, and few are quietly being served by those who already know how good they are. Choosing a tech career is very much like choosing from that buffet. If you only go for what everyone else is rushing toward, you might end up waiting too long and missing better options that are just about to become popular. Today's topic is which tech careers to pick in 2024. The main idea of this slide is that students should avoid technologies at the peak of their hype, where competition is intense and future oversupply is likely, and instead focus on those approaching maturity or long-term stability. Understanding this timing is critical because it can determine whether you enter a market at its opportunity peak or at its decline. Let's begin by looking at the hype cycle for enterprise networking in 2024. This graph helps us see which technologies are rising, peaking, or stabilizing in the networking world. Right now, areas like AI networking, network AI assistance, and service connectivity layers are at the peak of inflated expectation. Everyone is talking about them. Investors are pouring money in, and job demand seems high. But just like an overinflated balloon, this excitement cannot last forever. Once companies realize the limitations, hiring slows and consolidation begins. Students focusing only on these headline trends risk entering the market just as it cools down. Instead, attention should shift toward technologies climbing the slope of enlightenment or nearing the plateau of productivity, such as 5G, edge networking, or software-defined wide area network. These areas are moving past the hype and into practical deployment, meaning that companies are now looking for skilled engineers who can implement and optimize, not just experiment. Think of it as joining a construction crew after the blueprint phase. This is where the real building begins, and the jobs are steady. Next, let's examine the hype cycle for emerging technologies in 2024. This side of the chart captures newer fields like generative AI, large action models, and spatial computing. Generative AI, as you all noticed, is at the absolute peak of hype. Every industry claims to be AI-driven, and the job market is flooded with similar roles. This is exciting but also risky, like surfing a giant wave that might crash at any moment. If you join at the top without deep specialization, you might find that the market becomes saturated by the time you graduate. On the other hand, fields that are currently climbing but not yet overcrowded, such as AI simulation, digital twins, or AI supercomputing, are excellent areas to consider. They will reach maturity in the next few years, aligning perfectly with your graduation timeline. Think of these as seeds planted in fertile soil. They are not glamorous yet, but by the time they bloom, you will already have the expertise to lead, not follow. A good strategy for career selection is to identify technologies transitioning from research to implementation. For example, cloud-native web assembly, AI-driven network management, and quantum networking are not in the spotlight now, but they represent the next infrastructure wave. Enterprises are beginning to invest in these because they bridge existing systems with next-generation needs. It is like learning how to operate hybrid engines before electric cars take over. You position yourself for the future while still being relevant in the present. In communication engineering specifically, technologies such as 5G, private networks, network automation platforms, and edge computing are particularly promising. These fields require a combination of signal processing knowledge and software engineering, which perfectly fits your training. They are at the slope of enlightenment, where theory meets deployment, and companies are hungry for engineers who understand both hardware performance and network optimization. Now let's talk about timing, which is just as important as choosing the right technology. You have to think like an investor entering the market before it peaks. Joining a field when it is still growing gives you room to learn, experiment, and establish yourself before it becomes saturated. On the other hand, entering too early, when a technology is still in its research infancy, may leave you waiting for years before commercial opportunities appear. The key is to balance curiosity with practicality. For instance, while quantum computing sounds exciting, its commercial use is still at least a decade away. Instead, focusing on quantum communication or cryptography offers more immediate applications. Similarly, While AI ethics and regulation are currently small fields, they are expected to expand rapidly as governments introduce policies on responsible technology use. Choosing these supporting roles can be like playing a strategic game of chess. Rather than moving where everyone else goes, you move where the board will open next. It is also worth emphasizing that the technologies nearing maturity today will drive the job market stability in the next 5 years. This means focusing on systems integration, cybersecurity in 5G environments, and automation frameworks like ONAP and ORAN that we discussed in earlier slides. Companies are not just looking for innovators, but also for engineers who can make large-scale systems reliable, secure, and efficient. The glamorous stage of experimentation might get the headlines, but the long-term careers are built in the optimization and scaling phases. If we compare this to signal theory, it's like distinguishing between the transient and steady-state responses of a system. The initial hype is the transient spike, exciting but unstable, while the plateau represents the steady state where stability and productivity occur. You want your career to grow in the steady state region. Before we conclude, let me share one practical way to apply this insight. Every year, look at updated hype cycle reports and track which technologies are moving from hype toward implementation. Then, match those with your interests and academic strength. For communication engineers, this might mean keeping an eye on 6G research, AI-powered network analytics, or energy-efficient wireless systems. For those interested in computing, edge AI platforms, federated learning, and cloud orchestration tools are promising. Aligning your coursework, internships, and projects with these trends ensures that when the market demands those skills, you are already prepared. Remember, you are not just competing with classmates here in Taiwan, but with graduates worldwide. Timing your expertise correctly gives you an advantage that raw intelligence alone cannot guarantee. To summarize, choosing your tech career in 2024 is about reading the signals, not just following the noise. Avoid fields that are at the peak of inflated expectations, where the competition is fierce and the market is unstable. Instead, focus on technologies entering their slope of enlightenment or nearing productivity, where real opportunities lie. Understand that hype attracts crowds, but maturity builds careers. Your goal is not to chase what is loudest today, but to prepare for what will matter tomorrow. Just like in engineering, stability is achieved through balance. And the best engineers learn not only to build systems, but also to time their designs perfectly within the cycle of innovation. Imagine you are standing in a busy train station during rush hour. There are different kinds of passengers. Some are daily commuters rushing to work. Some are travelers with luggage moving slowly. And some are delivery workers carrying heavy packages. Even though everyone is in the same space, their needs and priorities are completely different. Designing a wireless network or evaluating a technology market is very similar. Not every user or sector requires the same speed, latency, or reliability, and understanding these differences is what determines whether a technology succeeds or fails. Today's topic is how to evaluate tech market demand. The key message of this slide is that understanding market diversity, user needs, and cost considerations is essential to assessing technologies like 5G and 6G, which serve both public and private sectors with very different expectations and applications. Let's start with the first key idea, that market diversity matters. Technologies such as 5G and 6G do not exist in a single universal form. They serve multiple markets at once. Public networks for general users and private networks designed specifically for enterprises or industries. Think of it like a road system. The public highways connect everyone, providing wide accessibility but with some traffic and general rules. In contrast, private industrial roads are like special lanes reserved for emergency vehicles or logistics trucks. They are optimized for speed, reliability, and security. In communication terms, public 5G networks must serve millions of users, streaming videos or playing games, while private 5G networks might support a smart factory where hundreds of robots communicate in real time. Each of these markets has unique technical and regulatory requirements, from bandwidth allocation to latency control. This diversity makes evaluation complex, because success in one area does not guarantee success in another. When engineers design or analyze a technology, they must ask, who is the end user? What is their environment? And what kind of service guarantees do they need? Now, let's consider the second point, that multiple user needs directly affect technology adoption. Different users, humans, IoT devices, or AI systems, have vastly different demands. It's like cooking for a large group where some people want spicy food, some prefer sweet, and others need gluten-free meals. You cannot serve a single dish for everyone. In telecommunications, a smartphone user cares about video quality and download speed, while a sensor in a smart city only needs to send tiny packets of data once every few seconds, but must do so reliably and with low power every few seconds, but must do so reliably and with low power. Meanwhile, AI-driven systems, such as autonomous vehicles, require ultra-low latency to make split-second decisions safely. Because of these differences, technology developers must customize their solutions for each segment. This is why 5G was designed with three main service types: enhanced mobile broadband for high data rates, ultra-reliable low-latency communication for mission-critical tasks, and massive machine-type communication for IoT. Each category serves a distinct user profile, and understanding these trade-offs helps engineers and businesses align their products with actual market needs rather than chasing abstract performance numbers. Next, we should examine how competition among technologies shapes market demand. Even within the same domain, multiple solutions often compete to meet similar needs. This competition can come from alternative wireless standards, software innovations, or even adjacent industries. Imagine a city where different transport systems, buses, subways, and bikes coexist. Each system works best for certain routes or passengers. Similarly, in networking, Wi-Fi 7, 5G, and private fiber networks overlap in some use cases. For instance, companies might prefer Wi-Fi for indoor environments due to cost and convenience, while they rely on 4G for outdoor or mobile operation. When evaluating market potential, engineers must analyze where their technology offers unique advantages and where competitors already dominate. If two technologies solve the same problem, the one offering better cost-performance balance or easier deployment will prevail. This competitive landscape constantly evolves, meaning that staying informed about complementary and rival technologies is as important as understanding one's own system. Successful engineers are not just inventors, they are also strategists who recognize when and where a solution fits best. The final aspect to discuss is cost and scalability, two factors that often determine whether a technology moves from prototype to real-world adoption. Even the most advanced solution can fail if it is too expensive or difficult to scale. Think of building a skyscraper with a brilliant design, but using materials so costly that no one can afford to replicate it elsewhere. In the telecom industry, cost considerations include spectrum licensing, infrastructure deployment, and operational maintenance. Public networks require massive investments in base stations, while private networks must justify their cost through improved efficiency and automation. The key challenge is finding the balance between technical ambition and economic feasibility. A technology that is slightly less powerful but cheaper and easier to deploy can often outperform a cutting-edge but unaffordable system. Engineers must therefore consider total cost of ownership, not just technical specification. The most sustainable innovations are those that scale effectively across multiple use cases and price points. Bringing these points together, evaluating tech market demands is both an analytical and creative process. You need to understand who the users are, what problems they face, what competing solutions exist, and whether the technology can be implemented cost-effectively. Looking at the hype cycle graph on this slide, you can see that not all technologies rise or fall in the same way. Some, like AI, networking, or network AI assistants, are still at the peak of inflated expectations, while others, such as edge networking or software-defined interconnects, are climbing the slope of practical adoption. This reminds us that market evaluation is not static. It changes as technologies evolve and as user expectations mature. To conclude today's discussion, understanding tech market demands means looking beyond the technology itself. It requires analyzing diversity among markets, differentiating between user types, assessing competing solutions, and balancing costs with scalability. 5G and 6G networks illustrate this complexity perfectly. They are not one-size-fits-all systems, but ecosystems that adapt to multiple industries and user profile. As future engineers, your task is to learn how to read these market signals, just as you interpret frequency responses or system behaviors in signal processing. In both engineering and economics, the key is to recognize the underlying structure beneath the noise. Those who can identify real demand amidst hype will not only design better technologies, but also shape the direction of innovation in the years to come. Imagine a massive earthquake strikes a city. Power lines are down, phone signals are jammed, and emergency services cannot communicate efficiently. In that moment, every second matters. Now imagine a team arrives, unfolds a compact 5G private network from their vehicle, and within minutes, all first responders are connected with high-speed, low-latency communication. Drones begin scanning the area, ambulances receive live patient data, and command centers coordinate in real time. That is the power of open architecture in public safety network. Today's topic is why use open architecture for public safety. The key idea of this slide is that open architecture in 5G private networks enables faster deployment, lower costs, and more reliable communication, which are vital for emergency response and smart city application. Let's begin with the concept of rapidly deployable 5G private networks. Traditional communication systems for public safety often rely on centralized infrastructure, which can take hours or even days to set up after a disaster. Open architecture changes this dynamic. It allows different vendors' components to interoperate, meaning a network can be assembled from modular parts, like building blocks that snap together instantly. Think of it like carrying a portable toolkit instead of a single heavy machine. Each tool has a purpose, but together they form a complete solution that can adapt to any situation. When an earthquake, flood, or wildfire strikes, a deployable 5G private network can be established locally without waiting for major carriers or external infrastructure. This agility ensures that communication remains functional when other systems collapse. In Taiwan, for instance, such technology could be a game changer for disaster-prone regions, where first responders need immediate and stable connectivity even in the most remote area. Next, let's discuss why open architecture is especially critical for mission-critical communication. When we say mission-critical, we mean systems where failure is not an option, like ambulances sending patient vitals to hospitals, firefighters navigating burning buildings, or police coordinating crowd control. These operations require ultra-reliable low-latency communication, also known as ULLC, which ensures that data reaches its destination almost instantly and without interruption. Open architecture allows these systems to be customized and optimized for specific emergency use cases. It's like tuning an orchestra for different performances. In a concert hall, you might prioritize harmony and acoustics, while in an outdoor festival, you amplify clarity and reach. Similarly, open networks allow engineers to fine-tune the balance between speed, coverage, and reliability depending on the environment. By integrating software-defined networking and network slicing, public safety teams can allocate specific portions of bandwidth exclusively for emergency communication, avoiding congestion from civilian traffic. This guarantees that life-saving data always gets through, even when everyone else's network is overloaded. Now let's move to how this architecture connects with smart city ecosystem. Modern cities are filled with sensors, cameras, and IoT devices that constantly collect data. During emergencies, these systems become invaluable. For example, traffic sensors can detect congestion and reroute emergency vehicles, while drones, equipped with 5G cameras, can transmit live video to command centers. Open architecture enables all these devices, built by different manufacturers and using different protocols, to communicate through standardized interfaces. It's like establishing a common language in a multinational rescue team. Without it, coordination would be chaotic. With it, every participant, whether human or machine, understands and responds instantly. This interoperability also extends to infrastructure sharing. Municipalities, energy companies, and hospitals can all link their private 5G systems to form a collaborative network during crises. The result is a resilient communication web that does not depend on a single operator, which dramatically increases overall reliability. Another advantage of open architecture lies in its economic and strategic impact. Deploying closed, proprietary networks can be extremely costly and slow because organizations must depend on one vendor for both hardware and software. Open systems, by contrast, allow multiple suppliers to compete, driving innovation and lowering costs. It's similar to how open source software democratized computing. Instead of paying a premium for exclusive solutions, governments and enterprises can build their own configurations based on standardized blueprints, often using locally produced components. This independence not only reduces spending, but also strengthens national security by avoiding over-reliance on foreign technology providers. Moreover, with open platforms, upgrades and maintenance can be done incrementally without replacing entire systems. In public safety, where budgets are limited and continuity is essential, this flexibility ensures that networks remain state-of-the-art without interrupting daily operation. If we look at the table on this slide, you can see how these principles extend beyond public safety into other sectors like manufacturing, energy, healthcare, and transportation. In manufacturing, 5G and edge processing enable remote-controlled robots and automated production lines, ensuring precision and safety. In the energy sector, ULLC networks monitor and protect smart grids in real time, preventing cascading failure. In healthcare, wearable IoT devices track vital signs, while 5G supports remote diagnosis and training for medical staff. In transportation, autonomous vehicles rely on MBB and ULLC services to communicate and navigate safely, while in media and entertainment, 5G allows real-time broadcasting and immersive virtual experiences. All these use cases share one core idea. Open architecture unites diverse systems into a cohesive network that can adapt to specific needs. Let's think about this from an engineering perspective. In signal processing, we often design systems to be robust against noise and unpredictable conditions. The same principle applies here. Open architecture builds robustness not by isolating components, but by allowing flexibility and redundancy. When one part fails, another can take over. It's like designing a control system with multiple feedback loops. If one sensor stops working, the system still maintains stability. This adaptability is exactly what makes open 5G architectures suitable for public safety, where conditions are uncertain, and quick recovery is vital. In summary, open architecture provides the foundation for reliable, efficient, and flexible communication systems that can serve both daily operations and emergency response. Rapidly deployable 5G private networks ensure that first responders can act immediately, while mission-critical optimization guarantees ultra-reliable, low-latency connection. Interoperability supports smart city integration, and open frameworks lower costs while boosting innovation and security. Together, these features make open architecture not just a technical choice, but a societal necessity. When disaster strikes, communication is the first lifeline, and open architecture ensures that this lifeline never breaks. For you as future communication engineers, this represents more than a design philosophy, it's a responsibility. The systems you create could one day decide how quickly help arrives, how efficiently cities recover, and ultimately, how many lives are saved. Imagine you are managing a busy train network in a large city. Every day, trains from different companies share the same tracks, carrying thousands of passengers. If all the trains use different signaling systems and incompatible rails, chaos would follow. Now imagine that one day, not only are the rails standardized so every train can run smoothly, but an intelligent control center is added. This system predicts delays, adjusts schedules automatically, and ensures the best traffic flow with minimal human intervention. The first improvement, the standardization of rails, represents O-RAN, while the Intelligent Control Center represents AI-RAN. Today's topic is how are O-RAN and AI-RAN different? The key idea is that O-RAN focuses on creating open and flexible networks by standardizing interfaces and allowing interoperability, while AI-RAN uses artificial intelligence to automate and optimize those networks for maximum performance and efficiency. Together, they represent two complementary directions in the evolution of wireless communication systems. Let's begin with O-RAN. The O in O-RAN stands for open, and that word captures its entire philosophy. Traditional radio access networks, or RANs, were closed systems where all equipment had to come from the same vendor. It's like being locked into a single car brand that only works with its own fuel, tires, and parts. If something broke, you had to go back to the same company for repairs, often at a high cost. O-RAN breaks that monopoly by defining standardized open interfaces between network components, such as the radio unit, distributed unit, and centralized unit. This means operators can now mix and match equipment from multiple suppliers. For example, a telecom provider might use antennas from one company, baseband processors from another, and network management software from a third, all working together seamlessly. This openness encourages innovation, reduces costs, and makes upgrades much easier. Instead of replacing an entire system, you can upgrade individual parts as technology evolves. In short, O-RAN turns the network into a flexible ecosystem rather than a closed fortress. Now let's talk about AI-RAN. If O-RAN standardizes the structure, AI-RAN gives it intelligence. Traditional networks operate reactively. They respond to problems after they occur. AI-RAN, on the other hand, predicts issues before they happen and adjusts the system proactively. It's like a self-driving car that can detect traffic patterns, anticipate congestion, and reroute itself before getting stuck. AI-RAN applies machine learning and data analytics to network management. It continuously collects data on signal strength, user density, and device behavior, then uses that data to optimize performance automatically. For instance, if the system detects that users are moving from an office district to a sports stadium, it can allocate more bandwidth to the stadium area before congestion starts. AI also helps reduce power consumption by turning off unused base stations during low traffic hours. This predictive and adaptive capability increases reliability, enhances user experience, and reduces operational costs. Essentially, while O-RAN focuses on who builds the network, AI-RAN focuses on how the network thinks. To see the difference more clearly, imagine O-RAN as the body of a human and AI-RAN as the brain. The body provides structure, flexibility, and movement, while the brain processes information, learns from experience, and makes decisions that keep the system efficient. Without the body, the brain has nowhere to operate. Without the brain, the body cannot adapt or improve. In practice, O-RAN and AI-RAN work hand in hand. O-RAN provides the modular and open foundation that allows multiple vendors and technologies to coexist, while AI-RAN leverages the openness to collect diverse data sources and apply intelligent control across the system. This synergy results in networks that are not only cheaper to build, but also smarter and more responsive to real-world conditions. Let's consider how this affects network operators. In the traditional telecom model, operators faced high capital expenditures and limited flexibility because proprietary hardware and software were tightly integrated. When new technologies emerged, they often had to replace entire systems, which slowed down innovation. O-RAN changes that by turning hardware into a commodity and shifting intelligence into software. Operators can scale faster and introduce new services without major overhauls. Meanwhile, AI-RAN builds on that foundation by improving asset utilization. It ensures that existing infrastructure is used as efficiently as possible, predicting demand patterns and reallocating resources dynamically. This combination leads to higher spectral efficiency, the ability to transmit more data over the same frequency band, and better energy management, two of the biggest challenges in modern communication networks. From a business perspective, this transition also shifts where value is created. In the old model, revenue centered on physical equipment like base stations and antenna. But as networks become more software-defined and AI-driven, the real value moves toward data analytics, automation tools, and service intelligence. You can see this reflected in the diagram on the slide. The base station market is shrinking in relative terms, with declining average revenue per user and increasing capital cost. Meanwhile, the AI infrastructure and applications market is expanding, generating more revenue and scalability. This represents the evolution of telecom from a hardware-centric industry to a data-driven ecosystem. In the future, companies that understand both open standards and AI optimization will lead the industry, bridging the gap between engineering and intelligence. Another important distinction between O-RAN and AI-RAN lies in their goals. O-RAN's main goal is interoperability. It ensures that multiple vendors can cooperate within the same system, which democratizes innovation and breaks down traditional silos. AI-RAN's main goal, in contrast, is self-optimization. It minimizes human intervention by letting the network learn from its environment and improve autonomously. Think of O-RAN as creating an open playground where everyone can bring their own toys, while AI teaches those toys how to play together harmoniously without constant supervision. This dynamic combination leads to faster innovation cycles, as AI models can analyze performance data from different vendors and suggest improvements that benefit the entire ecosystem. To put this in a practical context, imagine a large city during a major event, like a concert or a sports game. O-RAN enables multiple vendors' equipment to work together in setting up temporary network coverage, providing flexibility and cost saving. AI-RAN then steps in to analyze real-time traffic, adjust signal strength dynamically, and prevent network congestion before users even notice. Together, they create a network that is both open and intelligent, capable of adapting instantly to unpredictable situations. In conclusion, the difference between O-RAN and AI-RAN is like the difference between structure and intelligence. O-RAN provides the open modular framework that encourages diversity and flexibility, while AI-RAN introduces automation and predictive learning to enhance performance and efficiency. One makes networks easier to build and maintain. The other makes them smarter and more adaptive. Both are essential to the future of wireless communication, especially as we move toward 6G, where networks will not just connect devices but sense, learn, and evolve with their environment. As future communication engineers, your challenge will be to master both aspects, to design open systems that welcome collaboration, and to integrate intelligence that keeps those systems running at their best. This balance between openness and intelligence is what will define the next generation of global connectivity. Imagine you are driving on a highway filled with cars. Suddenly, the vehicle ahead of you brakes, and before you can react, your car automatically slows down, avoiding a collision. This is not magic, but intelligence at work, where sensors, data, and algorithms make split-second decisions faster than humans can. Now, imagine applying that same level of intelligence to communication networks. Instead of cars, think of millions of data packets moving through the network every second. What if the network itself could detect congestion, reroute data, or even repair itself before anything goes wrong? That is precisely what AI-RAN aims to achieve. Today's topic is why do we need AI-RAN? The key message of this slide is that AI-RAN takes open networks one step further by integrating artificial intelligence to automate operations, predict failures, and enhance both reliability and user experience. Something that traditional or even Open RAN systems cannot handle alone. Let's start with improved reliability. In conventional networks, when something goes wrong, like a sudden traffic spike or a failed base station, human engineers often have to step in, analyze logs, and manually reconfigure systems. That process can take minutes or even hours, which is unacceptable for modern applications that depend on real-time communication, such as autonomous vehicles or remote surgery. AI-RAN changes this by continuously monitoring the network and predicting problems before they happen. It's like having a doctor who can detect early symptoms and prescribe treatment before the patient even feels sick. Using machine learning models, AI-RAN can recognize patterns of congestion or hardware stress and automatically reroute data or adjust parameters to avoid service interruption. For example, if a base station starts showing signs of overheating, the system can reduce its workload and shift traffic to nearby cells before a failure occurs. This predictive capability not only reduces downtime, but also extends the lifespan of network equipment. In a world where connectivity is as vital as electricity, reliability is not just a convenience, it is a necessity, and AI-RAN ensures that the network remains resilient, even under extreme conditions. Now let's move to the next point, which is predictive maintenance and automation. Think of AI-RAN as a smart maintenance system for the entire network. Traditionally, engineers perform scheduled inspections or react after problems occur. It's like taking your car for servicing every few months, regardless of whether it needs it or not, or waiting for it to break down on the road. AI-RAN replaces this static approach with a dynamic one. By analyzing real-time data from antennas, servers, and baseband units, AI can estimate when a component is likely to fail and schedule repairs at the most convenient time. This is similar to how modern jet engines send performance data to ground control after every flight, allowing technicians to fix issues before they affect the next journey. In telecom, such predictive maintenance can prevent costly outages and minimize disruptions, especially in mission-critical applications like hospitals, airports, or emergency services. Furthermore, AI-driven automation can perform routine tasks such as bandwidth allocation, interference management, and software updates without human intervention. This means engineers can focus on innovation instead of manual troubleshooting, leading to faster adaptation and lower operational costs across the network. Next, let's consider how AI-RAN improves user experience, which is perhaps the most visible benefit to end users. When you open a video app or join a live online class, you expect instant and smooth connectivity. Yet, during peak hours, congestion often slows everything down. Traditional networks handle this reactively, but AI-RAN takes a proactive approach. It constantly learns from usage patterns and anticipates where and when data demand will increase. It's like a restaurant that prepares extra dishes right before lunch rush because it already knows how many customers will arrive. For instance, during a major sports event, AI-RAN can allocate extra capacity to nearby base stations even before the crowd gathers. During nighttime, it can conserve energy by shutting down unused cells without affecting users. By dynamically balancing resources, AI-RAN ensures that every user gets consistent speed and quality, even when the network is under pressure. This optimization is not just about faster downloads, but also about stability and fairness, ensuring that bandwidth is distributed intelligently among devices, users, and applications. In short, AI-RAN transforms the network into a living system that adapts to human behavior in real time. To understand why AI-RAN is so transformative, we should compare it with O-RAN. O-RAN opened the doors to multi-vendor collaboration and reduced costs through standardization, but it still relies heavily on human operators for network management. It's like having a beautifully designed orchestra where every musician can play together, but without a conductor to coordinate them dynamically. AI-RAN is that conductor. It listens to every instrument, the base stations, antennas, and data servers, and ensures they perform in perfect harmony. When one section gets too loud, AI lowers its volume. When another falls behind, it amplifies it. This orchestration ensures not only technical efficiency, but also operational harmony. The result is a network that not only functions well, but continuously improves itself through learning and adaptation. This makes AI-RAN especially valuable for emerging use cases like real-time robotic interaction, autonomous decision-making, and AI-assisted healthcare, where every millisecond counts. Looking at the examples on the slide, you can see how AI-RAN supports different industries. In robotics, it enables machines to interact seamlessly and make autonomous decisions without delay. In healthcare, it assists surgeons performing remote operations by guaranteeing stable and ultra-low latency connection. In logistics, AI-RAN ensures that fleets of autonomous robots communicate efficiently, reducing collision risks in warehouses. Even in data-driven applications like large language models used for confidential information retrieval, AI-RAN helps secure and optimize the underlying communication infrastructure. These examples show that AI-RAN is not just a technological upgrade, but a foundational step toward intelligent, context-aware connectivity that integrates communication into one unified system. To tie everything together, the need for AI-RAN stems from the growing complexity of modern networks. Open systems like O-RAN provide flexibility and scalability, but they also generate vast amounts of operational data that humans alone cannot manage efficiently. AI fills this gap by transforming raw data into actionable intelligence. It brings predictive awareness, automated optimization, and self-healing capabilities that keep networks reliable, efficient, and responsive. From a user's perspective, this means faster, smoother, and more dependable connectivity. From an engineering standpoint, it represents the evolution from managing networks manually to teaching them how to manage themselves. In conclusion, we need AI-RAN because the future of communication demands more than just openness. It requires intelligence. As networks become denser and applications more demanding, AI is no longer an optional enhancement. It is the brain that allows our digital nervous system to function effectively. AI-RAN ensures improved reliability through proactive detection and repair, predictive maintenance that prevents failures, and better user experience through intelligent resource allocation. It transforms networks from reactive systems into proactive organisms capable of learning and adapting. For you as future communication engineers, mastering AI-RAN will mean understanding how to make networks not only connect, but also think, ensuring that the systems we build can keep up with the speed, complexity, and intelligence of the world they serve. Imagine you are running a city's traffic control center. At first, the system is simple. There are a few major intersections, and human operators can manually adjust traffic lights to keep cars moving. But as the city grows, new roads, tunnels, and highways appear. Suddenly, manual control becomes impossible. Traffic jams form faster than people can react, and accidents occur because the system cannot adapt quickly enough. At this point, what you need is not more human controllers, but an intelligent automated system that can learn from data, predict congestion, and optimize the flow in real time. This transition perfectly mirrors what happens in telecommunications when we move from O-RAN to AI-RAN. Today's topic is when to move from O-RAN to AI-RAN. The key idea of this slide is that telecom operators should shift to AI RAN when networks become too complex for manual management, and when automation and predictive optimization become essential to maintain speed, reliability, and cost efficiency. Let's begin by understanding the signs of network complexity. In the early stages of deployment, O-RAN's open and flexible design works well because human engineers can still monitor, configure, and troubleshoot the system. However, as the number of connected devices increases and data traffic grows exponentially, the network becomes like an ever-expanding maze. Imagine trying to manage thousands of traffic signals across an entire nation by hand. It's not only slow, but impossible to maintain consistency. Frequent network issues, slow response times, and rising downtime are symptoms of this complexity. For instance, when a base station becomes overloaded, manual reconfiguration might take minutes, but user demands shift in seconds. That time lag causes service interruptions and poor user experience. If engineers find themselves spending more time fixing problems than innovating, it's a clear signal that the system has reached its limit. This is where AI RAN becomes necessary. It can handle these challenges by constantly learning from the network's behavior and adjusting parameters automatically, keeping everything stable and efficient without the need for constant human intervention. Next, consider how AI helps when human engineers struggle to keep up. Think of a hospital emergency room. When there are only a few patients, doctors can manage easily. But when a large-scale accident floods the hospital with dozens of critical cases, doctors need help prioritizing and organizing treatment. AI RAN plays a similar role for network. It doesn't replace human engineers. Rather, it assists them by taking over repetitive and time-sensitive tasks. For example, AI algorithms can instantly analyze thousands of performance metrics from different network layers, like signal strength, latency, or interference, and identify anomalies in milliseconds. Humans simply cannot process data at that speed or scale. Furthermore, AI can detect patterns that even experienced engineers might miss, such as subtle correlations between network congestion and environmental factors like weather or user mobility. It's as if AI provides an extra pair of eyes that never sleep, scanning every corner of the network and alerting humans only when necessary. This partnership between human intuition and machine precision ensures that networks stay ahead of problems rather than constantly reacting to them. Now let's talk about cost and performance. One of the main reasons to transition to AI RAN is efficiency. Managing large-scale networks manually consumes a lot of time, energy, and money. Each hour of downtime can cost millions of dollars in lost revenue for operators and businesses relying on connectivity. AI RAN addresses this by automating maintenance and optimizing resource allocation. For instance, it can predict which base stations will experience heavy loads and redistribute bandwidth before congestion happens, reducing wasted capacity elsewhere. It's like a smart power grid that redirects electricity to where it's needed most, instead of keeping all lights on all the time. This automation significantly lowers operational expenses because fewer human resources are required to perform constant monitoring and troubleshooting. Additionally, AI RAN improves performance by continuously fine-tuning network parameters in real time. It ensures that every part of the system operates at optimal efficiency, whether it's managing spectrum usage, balancing traffic between cells, or minimizing energy consumption during low demand period. Over time, this results in a self-optimizing network that not only performs better, but also becomes cheaper to operate. Customer satisfaction is another crucial factor that determines when to adopt AI RAN. In today's digital world, users expect seamless connectivity everywhere. At home, in transit, or even in crowded venues like stadiums. When they encounter lag, dropped calls, or unstable connections, their frustration reflects directly on the operator's brand reputation. Traditional systems often react too slowly to prevent these issues, but AI RAN's predictive capabilities change the game. It continuously monitors user behavior and anticipates demand fluctuation. For example, during a concert or sports event, AI RAN can detect rising network activity and allocate more capacity to the area before congestion starts. After the event, it automatically scales back to conserve energy. This adaptability leads to smoother user experiences and higher satisfaction level. In short, AI RAN turns reactive service into proactive management. It's like a restaurant that knows its customers so well that their favorite dishes are already being prepared before they even order. That level of anticipation builds trust and loyalty, which are critical in a competitive telecom market. The transition from O-RAN to A-RAN is not just a technical upgrade. It's an evolutionary step. O-RAN gives operators freedom by removing vendor lock-in and enabling interoperability, but AI RAN adds intelligence to that freedom. The shift typically happens when the scale and complexity of the network exceed what manual processes can handle. It's like moving from flying a small airplane with manual controls to piloting a jet that relies on autopilot for stability and efficiency. The human pilot remains essential, but focuses on strategy rather than micromanagement. Similarly, AI RAN allows engineers to focus on long-term optimization, innovation, and service design while the system manages the day-to-day adjustments automatically. Finally, we can summarize the decision process into a simple principle. Move from O-RAN to AI RAN when complexity outpaces control. When the number of connected devices, service types, and data traffic makes human-driven management unsustainable, AI RAN becomes the logical solution. It reduces operational costs through automation, enhances performance through predictive optimization, and boosts customer satisfaction through proactive adaptation. The transition doesn't replace human expertise. It amplifies it by giving engineers a smarter, faster, and more adaptive network foundation to work with. In conclusion, knowing when to move from O-RAN to A-RAN is about recognizing the limits of manual management and the opportunities offered by intelligence. As communication systems evolve towards 6G and beyond, the networks we design will no longer be static infrastructures but living, learning entities. AI RAN represents that transformation. It is the point where connectivity meets cognition, where the network doesn't just transmit information but understands how to deliver it better. For you as future communication engineers, the lesson is clear. Open networks build the foundation, but intelligent networks sustain the future. Imagine you are managing a busy airport. At first, everything runs smoothly because there are only a few flights. The controllers can manually guide planes in and out, and operations stay efficient. But as the airport grows, hundreds of aircraft arrive and depart each hour. The runways fill up, weather changes unpredictably, and ground traffic becomes chaotic. You quickly realize that manual coordination is no longer enough. What you need is a smart management system that predicts congestion, schedules landings automatically, and coordinates all movements in real time. This analogy captures what is happening in modern telecommunications. As networks expand and user demand skyrocket, the once manageable O-RAN environment begins to reach its operational limit. That brings us to today's topic. What remains in O-RAN? The key idea of this slide is that while O-RAN provides the open and flexible foundation for network innovation, it still struggles with complexity as networks scale. Many core management and coordination tasks remain within O-RAN structure, but as they become too intricate for manual operation, the transition toward AI RAN becomes inevitable. Let's start by examining the signs of network complexity that still exist in O-RAN systems. In theory, O-RAN offers modularity, allowing different vendors and components to interoperate. However, with every added device, connection, and service, the coordination between these elements becomes exponentially harder. Imagine a symphony where each musician plays from a different sheet of music. Even if every instrument sounds beautiful on its own, the performance turns chaotic without perfect synchronization. In O-RAN, managing thousands of interconnected radios, edge servers, and virtualized components requires enormous human effort. Frequent network issues, slower response times, and longer downtimes are symptoms of this complexity. For instance, When one cell tower becomes overloaded, engineers must manually balance the traffic load across multiple neighboring towers. This is manageable in small systems, but becomes nearly impossible when scaled across entire cities. As a result, human engineers spend more time troubleshooting than optimizing. O-RAN's openness empowers innovation, but it also multiplies the variables that must be controlled, revealing the system's vulnerability to operational overload. Next, let's discuss the growing challenge of human engineers struggling to keep up with network demands. Think of O-RAN management like trying to steer a massive ship with a small crew. At first, everyone knows their roles, but as the ship grows larger, the coordination between departments becomes slow and error-prone. In telecommunications, engineers must constantly monitor performance indicators, adjust configurations, and respond to unexpected changes in traffic flow. This task becomes even more demanding with emerging technologies like network slicing and edge computing, which require near-instant decision-making. Humans, limited by reaction time and bandwidth of attention, cannot manage such complexity effectively. Even with automation tools, the amount of data generated by O-RAN systems is too vast for manual analysis. This is where the need for AI-driven assistance becomes clear. AI can process millions of data points in real time, identify subtle performance degradations, and automatically adjust network parameters before users notice any problem. In essence, while O-RAN remains the skeleton of the system, AI-RAN provides the nervous system that senses, analyzes, and responds instantly. Now, let's consider the cost and performance implications that remain challenging in O-RAN environment. Open architecture does reduce dependency on proprietary vendors and lowers initial deployment costs. But ongoing maintenance and optimization are expensive when handled manually. It's like owning a car that is affordable to buy but costly to maintain because every part needs separate attention. Engineers must constantly update software, balance loads, and tune parameters, which consumes both time and resources. Downtime or inefficient configuration translates directly to financial loss. Moreover, because networks are becoming increasingly heterogeneous, with small cells, macro cells, IoT devices, and private 5G systems all coexisting, the number of potential fault points multiplied. AI-RAN mitigates this by automating maintenance and continuously optimizing performance. It's like having a self-diagnosing car that schedules its own repairs before breaking down. The result is a dramatic reduction in operational costs and higher overall reliability. However, until AI capabilities are fully integrated, O-RAN operators still rely heavily on manual management, limiting their ability to scale efficiently. Another aspect that remains in O-RAN is the limitation of real-time control and adaptation. While O-RAN introduced the concept of the RIC, or RAN Intelligent Controller, it primarily functions as a coordination layer rather than a fully autonomous decision-maker. It collects metrics, enforces policies, and executes predefined rules, but it does not truly learn or predict future network states. Think of it like a pilot flying with instruments but without autopilot. The pilot can respond to turbulence but cannot predict it until it happens. This reactive approach leads to slower adaptation, particularly in dynamic environments like dense urban areas or large events where network conditions change rapidly. AI-RAN, on the other hand, integrates predictive models that anticipate congestion, adjust resource allocation, and even simulate multiple decision outcomes before choosing the best one. This shift from reactive to proactive control represents the biggest step forward in network intelligence, yet many operators are still operating in a mixed O-RAN model where partial automation coexists with human supervision, resulting in performance that is functional but not yet optimal. The diagram on the slide illustrates this transitional state. At the base, we see the O-RAN digital twin environment, which simulates network conditions and traffic behavior. Above it, components like the near real-time and non-real-time RICs manage communication between radio units and centralized function. This architecture allows for data collection and limited automation through ZAPs and RAPs, But the true intelligence, machine learning algorithms that can train, predict, and optimize in real time, remains external or experimental. In other words, the pieces of the puzzle exist within ORAN, but they are not yet fully connected. It's like having all the hardware for a self-driving car, but still relying on a human driver, because the AI system is only partially integrated. As we bridge toward AI-RAN, many of these ORAN elements will remain foundational. The open interfaces, virtualized components, and modular design will not disappear. They will simply evolve to support greater automation and learning capability. The difference will lie in how decisions are made. In ORAN, decisions follow rules written by humans. In AI-RAN, decisions emerge from patterns discovered by machine. This shift will redefine not just how networks operate, but also how engineers work, moving from direct control to intelligent supervision. To conclude, what remains in ORAN is the essential openness and flexibility that made it revolutionary, but also the inherent complexity that limits its scalability without intelligent. Manual management, even supported by advanced interfaces, cannot keep pace with modern network demands. Engineers continue to face issues of response time, maintenance cost, and limited adaptability. ORAN provides the architecture. AI-RAN provides the awareness. The future of telecommunications lies in combining the openness of ORAN with the predictive power of AI. For you, as future engineers, understanding this balance is crucial. The systems you design must not only connect people, but also learn from them, evolving in real time to meet the needs of an increasingly connected and intelligent world. Imagine walking into a modern city where everything seems to operate seamlessly. The traffic lights adjust themselves based on real-time flow. Garbage trucks arrive only when bins are full, and the power grid intelligently reroutes energy during peak hour. Now imagine that this level of intelligence also applies to communication network. Instead of engineers constantly tuning parameters and fixing issues, the network itself can predict problems, balance loads, and adapt to user demand automatically. That is the promise of AI-RAN. Today's topic is, where can AI-RAN provide benefits compared to traditional ORAN data? The key idea of this slide is that while ORAN revolutionized telecommunications by making networks open and flexible, AI-RAN takes it a step further by using artificial intelligence to bring automation, prediction, and optimization to every layer of the system. This integration of AI not only enhances performance, but also unlocks new possibilities that traditional ORAN alone cannot achieve. Let us begin with the foundation. ORAN focuses on openness and interoperability. In a traditional closed system, all components, from antennas to software, came from a single vendor. Much like buying a car that can only be repaired or upgraded at one exclusive workshop. ORAN changed that model by introducing standardized interfaces that allow multiple vendors to collaborate. Now operators can build a network using the best parts from different manufacturers, mixing and matching, like assembling a high-performance computer from various brands. This openness reduces costs, encourages competition, and accelerates innovation. For example, a telecom company can purchase baseband units from one supplier and radio units from another, knowing they will work together seamlessly. However, while ORAN improves flexibility and scalability, it still relies heavily on human intervention for management and optimization. Engineers must monitor performance, detect issues, and adjust settings manually. As networks grow larger and more complex, this human-centered model begins to show its limits, paving the way for AI to step in. Now, let us look at AI-RAN, which builds upon ORAN's structure but adds intelligence to its operation. The key difference lies in automation and learning. AI-RAN continuously analyzes data from across the network, signal strength, latency, traffic patterns, and makes dynamic adjustments to ensure optimal performance. You can think of ORAN as a smart home where you control everything through an app, while AI-RAN is the version where the home learns your habits and adjusts automatically. For instance, if the network detects that users in a certain area are streaming videos heavily, AI can predict congestion and allocate additional bandwidth before quality degrades. It can also identify potential hardware failures through anomaly detection, scheduling maintenance before a breakdown occurs. These capabilities improve both reliability and efficiency, reducing downtime and operating costs. More importantly, AI RAN introduces a proactive mindset into network management, shifting from reactive problem solving to continuous self-optimization. Let's go deeper into how AI RAN transforms network utilization, starting with the concept of AI and RAN. This approach involves AI and RAN sharing same infrastructure. Imagine a city where both public transportation and emergency vehicles use the same roads, but traffic lights prioritize each vehicle type depending on urgency. Similarly, in AI and RAN, the infrastructure is designed so that communication resources can be dynamically shared between standard network operations and AI computation tasks. This greatly improves asset utilization because the same hardware can support both connectivity and intelligence. When network traffic is low, idle computing resources can be redirected for AI model training or optimization tasks. Conversely, during high demand periods, resources are shifted back to prioritize user connectivity. This adaptability maximizes return on investment while maintaining high service quality. Next, we have AI on RAN, where AI applications are enabled directly by the RAN infrastructure. This model allows entirely new kinds of services that rely on real-time intelligence. Think of it as turning the network itself into a platform for AI-driven applications, not just a channel for data transfer. For example, autonomous vehicles can communicate with nearby base stations that process sensory data locally, allowing faster decision-making. Similarly, augmented reality and industrial automation systems benefit from AI on RAN by accessing low-latency computation close to the user. It's like having a mini data center at every base station capable of running AI applications in milliseconds. This not only reduces dependence on distant cloud servers, but also opens new business opportunities where telecom providers can offer edge-based AI services directly to enterprises and consumers. AI on RAN, therefore, extends the role of the network from a passive service provider to an active intelligence hub. Then there is AI for RAN, which represents AI's role in enhancing the efficiency of the RAN itself. In this model, AI is not just coexisting with the network, it is actively optimized. Picture a symphony orchestra where AI serves as the conductor, ensuring that each instrument plays at the right tempo and volume for perfect harmony. AI for RAN uses learning algorithms to improve spectral efficiency, manage interference, and fine-tune resource allocation across the radio spectrum. For instance, AI can dynamically adjust modulation schemes or power levels to match the real-time conditions of the environment. In dense urban areas where users move rapidly between cells, AI can predict handovers and minimize dropped connection. In rural regions, it can optimize coverage using minimal power, extending network reach while conserving energy. This adaptive intelligence allows operators to achieve higher throughput and better quality of service without expanding physical infrastructure, making the network not only smarter, but also greener. If we compare AI RAN to O-RAN, the distinction becomes clear. O-RAN provides the foundation, the open, modular framework that enables flexibility and vendor diversity. AI RAN builds on that foundation by adding the brainpower needed to manage complexity at scale. It is the difference between a network that can be built by anyone and a network that can run itself efficiently once built. From an engineering perspective, AI RAN bridges the gap between communication and computation, creating a feedback loop where data informs decision-making and decisions continuously refine performance. Edis, S, T, it, in, or else. This cycle of learning and adaptation marks a significant step toward autonomous networking, where systems evolve over time without manual intervention. To put this into perspective, consider how these models translate into practical advantages. AI and RAN ensures that infrastructure investment is maximized through dual-purpose use. AI on RAN unlocks new revenue streams by enabling real-time AI applications at the edge. AI for RAN drives continuous improvement in network performance, ensuring that resources are used efficiently and sustainably. Together, these benefits redefine how we view the radio access network, not just as a communication backbone, but as a living system that senses, learns, and optimizes itself. To conclude, AI RAN provides clear advantages over traditional O-RAN by bringing automation, prediction, and intelligence into the core of network operation. O-RAN's open architecture laid the groundwork for flexibility and innovation, but as networks become denser and more dynamic, I-RAN becomes essential for maintaining efficiency and user satisfaction. Whether through shared infrastructure, new application capabilities, or enhanced spectral efficiency, AI transforms the network from a reactive system into a proactive, self-managing ecosystem. For you as future communication engineers, the lesson is to think beyond building networks that connect devices. The challenge of the next decade is to design networks that can think, adapt, and evolve. AI RAN is the step that turns connectivity into intelligence, and intelligence into the foundation of a truly smart communication world. Imagine standing at a busy city intersection filled with vehicles, pedestrians, and cyclists. Cameras are capturing every angle, traffic lights are adjusting dynamically, and sensors are monitoring air quality. The city seems alive, responding instantly to every movement and event. Now ask yourself, where does all this data go, and how can it be processed fast enough to make real-time decisions, like turning a traffic light green to let an ambulance pass? This is where AI on RAN becomes the key. Today's topic is what in AI on RAN. The main idea of this slide is that AI on RAN refers to running artificial intelligence applications directly on the radio access network infrastructure, enabling real-time data analysis and smart city services with low latency, high bandwidth, and strong security. It represents the next step in the integration of communication and computation, bringing intelligence closer to where data is generated instead of relying solely on distant cloud servers. Let's begin with the concept of real-time video analysis. In modern urban environments, countless cameras continuously capture footage for applications like traffic management, crowd control, and public safety. Traditionally, this video data would be sent to a remote data center for processing, but that introduces delay due to transmission distance and limited bandwidth. AI on RAN changes this by placing computation directly at the edge of the network, close to the cameras and sensors. Think of it as moving the brain closer to the eyes, allowing instant reactions instead of waiting for signals to travel all the way to the spine and back. By running AI inference directly on the RAN, the system can identify objects, detect anomalies, or track motion within milliseconds. For example, if a car runs a red light or a crowd forms unexpectedly, AI on RAN can immediately alert authorities or adjust traffic patterns. This capability has already been proven in several smart city pilot projects where AI models process live video streams locally, achieving faster response times and reducing backhaul traffic. Now let's explore how this extends to smart city monitoring. A smart city is much more than just cameras and traffic lights. It includes air quality sensors, energy grids, public transport systems, and even water management. Each of these components generates continuous data that must be processed and acted upon quickly. Deploying AI within the RAN allows these tasks to be distributed across the network instead of being centralized. It's like giving every neighborhood its own small control center that can handle local issues before they escalate. For instance, if a sensor detects rising pollution in a certain district, the local AI on RAN node can activate ventilation systems or alert nearby factories to adjust emissions immediately. Similarly, if vibration sensors on a bridge detect structural stress, the network can trigger inspections without delay. This kind of responsiveness transforms cities from static systems into dynamic ecosystems that constantly adapt to their surrounding. The integration of AI and communication at the network edge creates a foundation for safer, cleaner, and more efficient urban living. Another key advantage of AI on RAN lies in its low latency. In communication systems, latency refers to the delay between sending and receiving data. The closer we bring computation to the user, the shorter this delay becomes. Think of it like ordering food from a local restaurant instead of one across the city. You get your meal faster because it doesn't have to travel far. In the same way, AI on RAN eliminates the need to send raw data to remote servers, process it, and send results back. This is particularly critical for applications like autonomous driving or telemedicine, where milliseconds can determine success or failure. Imagine a self-driving car approaching an intersection. If it depends on cloud-based AI, even a slight delay could cause a collision. But with AI on RAN, decisions happen locally, ensuring near-instant communication between vehicles, traffic systems, and pedestrians. This edge intelligence enables the kind of real-time coordination that future smart transportation networks will depend on. Equally important is high bandwidth, another strength of AI on RAN. As the number of connected devices grows, so does the demand for data transmission. Video streams, IoT sensors, and AR or VR applications all require enormous amounts of bandwidth. Traditional networks struggle when all this data must travel long distances to centralized data centers. By processing information at the RAN level, only the most essential data needs to be transmitted. It's like sorting mail at the local post office before sending it to the central hub. Unnecessary traffic is filtered out early, freeing capacity for more critical information. This localized data handling not only improves speed, but also reduces the overall load on the network backbone. Furthermore, since AI on RAN operates directly where wireless signals are transmitted and received, it can dynamically allocate spectrum resources based on real-time demand, further improving efficiency. The result is a network that is not just faster, but smarter, capable of optimizing itself as traffic patterns change. Security is another domain where AI on RAN offers significant advantages. When sensitive data is processed closer to its source, the risk of interception or leakage during transmission is greatly reduced. It's similar to keeping your personal documents in a locked drawer instead of sending them across town for storage. In applications involving facial recognition, financial transactions, or confidential communications, maintaining data privacy is essential. AI on RAN ensures that raw data, such as unprocessed video or sensor information, never leaves the local network. Only the analyzed results, stripped of sensitive details, are transmitted to central systems if needed. This distributed security model aligns perfectly with modern privacy regulations and public concerns about data misuse. By combining high security with low latency, AI on RAN provides a trustworthy foundation for future digital services in areas like healthcare, law enforcement, and industrial automation. Finally, let's talk about distributed computing, which is the architectural backbone of AI on RAN. Instead of concentrating all processing power in a few large data centers, AI on RAN spreads computation across many smaller nodes within the network. You can imagine it as replacing a single giant power plant with a network of smaller renewable energy sources distributed throughout the city. Each node can operate independently or collaborate with others when needed. This not only improves resilience, since the failure of one node doesn't cripple the system, but also makes scaling easy. As new AI applications emerge, operators can deploy additional edge nodes without major infrastructure changes. Distributed computing also reduces energy consumption by processing data locally, lowering the amount of power required for long-distance transmission. In short, it's an architecture that mirrors the way living organisms work, decentralized yet coordinated, efficient yet adaptable. When we combine all these features, real-time video analysis, smart city monitoring, low latency, high bandwidth, strong security, and distributed computing, we see that AI on RAN is not just a technical upgrade, but a paradigm shift in how we design and operate networks. It brings intelligence to the very edge of connectivity, empowering cities, industries, and individuals to make faster, smarter, and safer decisions. To summarize, AI on RAN transforms the radio access network from a passive conduit of information into an active participant in computation and decision-making. For you as future engineers, this represents a new frontier where communication systems are no longer just about transmitting data, but about understanding it instantly and acting upon it. The networks of the future will not merely connect people, they will think alongside them. Imagine sitting in your living room and talking to your doctor, but it feels as if they are standing right in front of you. You can see their gestures, feel their presence, and even sense the tone and rhythm of their speech as if you were face to face. Or imagine working alongside a robot that understands not just your commands, but also your intent, moving in perfect sync with your action. These scenes may sound futuristic, but they represent the world that 6G and artificial intelligence will create. Today's topic is what AI applications will 6G offer. The key idea of this slide is that 6G will use artificial intelligence to enhance communication between humans and machines, improve network performance, and enable valuable services such as digital healthcare and smart industry. In essence, AI will become the central nervous system of the 6G network, transforming it from a communication tool into an intelligent partner that understands, reacts, and learns. Let us begin with the first idea: human and machine interaction. One of the most exciting promises of 6G is intelligent telepresence, which allows people to interact remotely in ways that feel lifelike and natural. Current video calls are like looking through a window, but 6G aims to open the door entirely. Using AI-driven holographic communication and ultra-high bandwidth, future telepresence systems will capture fine details such as body language, facial expressions, and even subtle gesture. It's like replacing a postcard with a living 3D version of the person. Imagine attending a class or business meeting where everyone appears as full-scale holograms, able to move and respond in real time. Beyond human-to-human interaction, AI also enables seamless collaboration between humans and machines. Robots will no longer require strict programming for each task. Instead, they will interpret human intent through AI-enhanced sensors and respond intuitively, just like a colleague anticipating your next move. This merging of human intuition and machine precision will transform industries such as manufacturing, logistics, and healthcare, where humans and robots will coexist as synchronized partners. Next, let's explore enhanced network and service applications. As networks become more complex and interconnected, AI will be the key to maintaining efficiency and reliability. One major area of impact is digital healthcare. Imagine a wearable device that not only tracks your vital signs, but also analyzes long-term health patterns using AI and alerts your doctor before symptoms even appear. In 6G, the combination of massive bandwidth and ultra-low latency means medical imaging or real-time diagnostics can be performed instantly, even from remote areas. For instance, AI-driven 6G systems could support remote surgery with precision so fine that the surgeon's hand movements are mirrored exactly by robotic instruments across the world. Another important application lies in smart industry. AI integrated with 6G networks will enable automated inspections, predictive maintenance, and precise 3D tracking of industrial processes. It's like having a digital twin, a virtual copy of an entire factory that constantly monitors and optimizes operation. This not only improves productivity, but also reduces downtime, energy consumption, and waste. The synergy between AI and 6G will make industries more efficient, responsive, and sustainable than ever before. Let's move on to the concept of enhanced human communication. In 6G, communication will extend far beyond the exchange of voice and text. AI will make it possible to share sensations, emotions, and even thoughts in a digital form. This is known as multimodal communication, where information from multiple senses, sight, sound, and touch, is combined to create a rich, immersive experience. Picture a scenario where a musician performs in one country and audiences elsewhere not only hear the music, but feel the vibrations of the instruments as if they were in the same concert hall. Or consider immersive holographic telepresence, where you can attend a family gathering from another continent and feel as though you are physically there. These experiences require not just higher bandwidth, but intelligent systems capable of processing and synchronizing massive amounts of sensory data in real time. AI will also help translate emotions and context, enabling communication that goes beyond words. For example, AI algorithms could interpret tone and facial expressions to adjust the response of virtual assistants, making digital interactions more natural and human-like. In short, enhanced human communication in 6G will dissolve the barriers between physical and digital worlds, creating connections that feel truly personal. Now let's turn to enhanced machine communication. While 5G already supports billions of devices, 6G will connect trillions, forming an ecosystem where machines constantly interact, learn, and evolve. AI will make this ecosystem intelligent and self-organizing. Think of it as a society of machines that cooperate like a colony of ants, each performing small tasks that contribute to a larger goal. In a smart city, for example, AI-enabled sensors could coordinate traffic lights, public transportation, and energy grids, simultaneously optimizing efficiency across the entire system. This concept also applies to industrial robots, or cobots, that work alongside humans. Instead of requiring centralized control, these robots will communicate directly with one another through AI-enhanced networks, forming what is called a robot network fabric. This allows them to coordinate actions in real time, adapting to changes instantly. Imagine autonomous delivery drones that reroute themselves to avoid bad weather or congestion without needing human input. By embedding AI into the communication fabric itself, 6G ensures that machines not only exchange information, but also understand and act on it intelligently. Finally, let's discuss enabling services powered by AI in 6G. Beyond communication and automation, AI will transform how we experience and manage our environment. In the realm of smart cities, AI will provide integrated systems for environmental monitoring, infrastructure maintenance, and energy management. For example, street lights could adjust brightness based on pedestrian activity and weather conditions, while AI algorithms predict and prevent electrical faults before they occur. In transportation, 6G networks will support ultra-accurate 3D positioning systems for autonomous vehicles, ensuring centimeter-level precision, even in complex urban environments. In healthcare, AI-driven 6G services will enable continuous monitoring of patients, real-time emergency alerts, and personalized treatment recommendations based on data analysis. All of these services rely on AI's ability to process massive data streams instantly and make autonomous decisions with minimal delay. If we compare this to a human brain, 6G acts as the body's nervous system, transmitting signals at lightning speed, while AI serves as the brain, analyzing and directing those signals intelligently. When we put all these ideas together, it becomes clear that AI in 6G will redefine communication as we know it. It will bridge humans and machines, merge physical and digital realities, and create networks that are not just fast, but deeply intelligent. From lifelike telepresence and collaborative robots to predictive healthcare and self-optimizing industries, AI will turn connectivity into a form of cognition. As future engineers, you will play a vital role in designing these intelligent systems, ensuring they are efficient, ethical, and accessible. To conclude, 6G will not simply connect devices, it will connect intelligence. It represents a world where communication is no longer limited to exchanging information, but extends to sharing, understanding, emotion, and purpose. A world where networks learn, adapt, and grow alongside us. Imagine walking into a modern office where every desk has its own computer, but each machine is dedicated to only one task. One computer handles emails, another runs spreadsheets, and yet another is used just for internet browsing. It would look impressive, but terribly inefficient, wasting both power and space. Now imagine combining all these tasks into a single powerful system that can handle everything dynamically, assigning resources wherever they are needed most. This is the core idea behind AI and RAN. Today's topic is what an AI and RAN. The main message of this slide is that AI and RAN integrates artificial intelligence and radio access network functions on the same hardware, improving how networks perform, saving costs, and enabling faster, more efficient responses. This concept represents the fusion of communication and computation, bringing intelligence directly into the network infrastructure, rather than treating it as a separate component. Let's begin by understanding why combining AI and RAN makes better use of hardware. Traditionally, RAN equipment and AI processing systems operate on separate platforms. RAN hardware manages radio signals, modulation, and data transmission, while AI servers handle analytics and optimization. This separation is similar to having two kitchens in one house, one just for cooking rice and the other for making soup. It works, but it's unnecessarily complex and costly. AI and RAN changes this by running both tasks on a unified system, allowing the same processors, memory, and network resources to serve multiple purposes. For example, the same edge server that handles 5G communication can also process AI workloads like traffic prediction or network optimization. This integration eliminates the need for additional servers and reduces energy consumption. From an engineering perspective, it also simplifies management, since fewer devices mean fewer points of failure. By sharing infrastructure, telecom operators can cut capital expenditure and streamline maintenance, achieving higher efficiency without sacrificing performance. Now let's move to the second point: faster network responses. One of the biggest advantages of AI and RAN is its ability to process data close to where it is generated. In traditional systems, information must travel long distances to centralized data centers for analysis before returning with instructions. This process introduces latency, which is like sending a question by mail and waiting days for the reply. AI and RAN solves this by performing AI inference right at the edge of the network, near the antennas or base station. Think of it as having a local assistant who can answer your questions instantly instead of relying on a distant expert. By reducing the distance data needs to travel, the system minimizes delays and provides near real-time reaction. This is crucial for applications such as autonomous vehicles or industrial automation, where even milliseconds matter. For instance, in a smart factory, AI and RAN can detect and correct production line issues immediately, preventing costly downtime. This proximity between intelligence and connectivity marks a fundamental shift from reactive to proactive network management. Another key benefit of AI and RAN is its impact on user experience. When AI tasks are executed within the same infrastructure that delivers communication, the system can respond dynamically to changes in demand. Imagine a concert stadium filled with thousands of people, streaming videos and sharing content simultaneously. A traditional network might struggle, leading to buffering and slow upload. But with AI and RAN, the network can sense congestion, predict user behavior, and reallocate resources instantly. It's like a smart traffic system that reroutes cars automatically to avoid bottlenecks. The result is smoother connectivity, consistent speeds, and an overall better experience for users. This responsiveness is particularly valuable for emerging services such as augmented reality or immersive telepresence, which require both high bandwidth and low latency. By embedding AI directly into the RAN, the network becomes not just faster, but also adaptive, learning from real-time conditions to continuously optimize itself. Furthermore, AI and RAN promotes a more sustainable and scalable infrastructure. As networks evolve from 5G to 6G, the number of connected devices and data volume will continue to rise exponentially. Building separate systems for AI and communication would be impractical and environmentally costly. By combining both on the same hardware, operators can maximize energy efficiency and reduce carbon emissions. It's like upgrading a power plant to run on multiple fuel sources instead of building two separate ones for each type of energy. In addition, this integrated architecture makes it easier to scale up services. When new AI applications emerge, such as predictive maintenance for drones or adaptive learning in smart classrooms, they can be deployed directly on existing RAN nodes without major hardware changes. This flexibility accelerates innovation while keeping operational costs under control. The architecture of AI and RAN also enhances data security and privacy. Since data is processed locally instead of being sent to distant cloud servers, there are fewer opportunities for interception or breaches. This is especially important in sectors like healthcare, defense, and finance, where sensitive information must remain confidential. It's like having a secure vault in your house instead of storing valuables in a remote warehouse. Local processing ensures that personal data, such as medical scans or financial transactions, can be analyzed safely within the same network where it was generated. At the same time, AI algorithms can still share anonymized insights across the broader system, balancing privacy with collective intelligence. This design principle aligns with the growing global emphasis on secure and ethical data handling, ensuring that the benefits of AI are delivered responsibly. If we look deeper into the technical side, AI and RAN relies on advanced computing resources such as GPUs, FPGAs, and cloud edge collaboration. These technologies enable parallel processing and adaptive resource allocation, meaning the system can decide in real time whether a task should be handled locally or offloaded to the cloud. It's like a smart delivery network that decides which packages to handle in-house and which to outsource based on urgency and size. This flexibility not only improves performance but also ensures that network resources are used efficiently, preventing overload in any single component. As AI models grow larger and more complex, this distributed computing capability becomes essential for balancing performance with energy use. To tie everything together, AI and RAN represents the convergence of two powerful domains: artificial intelligence and radio access networks on a single unified platform. It achieves better hardware utilization by sharing infrastructure, provides faster responses by processing data closer to the source, improves user experience through adaptive optimization, and ensures security while enabling scalability. In simple terms, AI and RAN transforms the network from a collection of hardware boxes into an intelligent organism that senses, thinks, and acts in real time. For you as future communication engineers, this concept challenges the traditional boundaries between hardware, software, and intelligence. It invites you to design systems where computation and communication coexist seamlessly, where efficiency meets adaptability, and where networks become active participants in the data they transmit. In conclusion, the essence of AI and RAN lies in its integration. By merging AI computation and RAN operation within the same hardware, we move toward a future where networks are no longer passive channels, but intelligent infrastructures capable of making decisions, predicting outcomes, and optimizing themselves continuously. This evolution will shape the foundation of 6G and beyond, redefining what it means for a network to be both efficient and intelligent. As engineers, your mission will be to build this next generation of networks, systems that not only connect the world, but also understand it. Imagine you are attending a music concert in a massive stadium. Thousands of people are using their phones at the same time to upload photos, stream videos, and message friends. Each person's device is connected to a base station, just like different instruments playing their own melodies. But without a conductor, the sound would become noise. In the same way, A network without intelligent coordination struggles with interference, delays, and inefficiency. What if the network itself could learn to conduct this orchestra, predicting which connections need more resources, and when to hand users off smoothly between cells? That is precisely what AI for RAN does. Today's topic is what in AI for RAN. The main idea of this slide is that AI for RAN refers to using artificial intelligence to enhance the performance, efficiency, and coordination of radio access networks by optimizing how individual cells operate and how multiple cells collaborate with each other. Let's start with the first key point: full-stack AI acceleration for individual cells. In traditional networks, each cell operates with fixed algorithms that manage scheduling, resource allocation, and modulation. It's like having a train system with a timetable that never changes, even if more passengers show up or weather conditions shift. AI for RAN introduces intelligence at every layer of the stack, from the high physical layer to the medium access control and higher network layer. This means the system can learn and adapt based on real-time traffic and channel condition. For instance, AI can predict which frequency bands will experience interference and preemptively adjust power levels or scheduling. Similarly, at the PHY layer, AI models can enhance channel estimation, making the system more robust in challenging environments like urban canyons or high-speed trains. Imagine if your smartphone could sense network congestion before it happens and switch channels automatically without you noticing. That is the kind of intelligence AI for RAN brings. By embedding AI into each component of the radio access network, we move from static control to dynamic optimization, where every cell acts like a self-learning node that continuously improves its performance. The second concept is about scheduler and channel estimation optimization. Scheduling in a wireless network is much like assigning lanes in a swimming competition. Each user competes for limited frequency and time resources, and the scheduler's job is to allocate them fairly and efficiently. Traditional schedulers use mathematical models based on predefined assumptions, but these models cannot adapt quickly to changing real-world conditions. AI-based scheduling, however, learns patterns from historical data and real-time feedback, predicting traffic demand with high accuracy. It can dynamically allocate bandwidth to users with higher data needs or better channel quality, maximizing spectral efficiency. Similarly, channel estimation, which determines how the signal propagates through the air, can be dramatically improved through AI tools. Instead of relying solely on pilot signals and linear estimation, AI can predict channel states using deep learning models trained on massive datasets. It's like having an experienced pilot who can sense turbulence before it happens. This makes the network more reliable and reduces latency, ensuring that every bit of spectrum is used effectively. Next, let's move to intercell coordination, where multiple base stations cooperate to deliver seamless service. In a city, you can think of each cell tower as a neighborhood power grid. If one area suddenly experiences high demand, power needs to be balanced among neighboring grids. AI for RAN enables this type of collaboration by allowing base stations to share data and decisions in real time. Through AI, the network can coordinate handovers when a user moves from one cell to another so smoothly that users never experience interruption. This is especially important for autonomous vehicles or drones that move quickly across multiple coverage zones. AI can also handle interference between adjacent cells, predicting overlapping signals and adjusting beamforming patterns accordingly. The result is a network that behaves not as a collection of isolated cells, but as a single, unified system. This intercell intelligence also supports advanced techniques like enhanced distributed MIMO, where antennas from multiple base stations work together to serve users cooperatively. It's like several Wi-Fi routers forming a team to ensure that your device always has the strongest possible connection, no matter where you move. Now let's discuss some specific AI for RAN technologies that drive this coordination, such as non-collocation carrier aggregation, NTD, full duplex. Non-collocation carrier aggregation allows a user device to connect to different frequency bands from separate cell sites at the same time. Traditionally, this is managed by static algorithms that may not account for dynamic variations in load or signal strength. AI, however, can analyze real-time network data to decide which carriers should be combined for optimal throughput. This improves both speed and reliability without increasing power consumption. Similarly, TDD Full Duplex, which allows simultaneous transmission and reception on the same frequency, faces challenges like self-interference. AI-based signal processing can model and cancel these interferences more efficiently than traditional approaches, enabling higher capacity. Together, these advancements ensure that the network uses spectrum resources more intelligently and efficiently. Imagine if traffic lights could adapt instantly to changing vehicle flow, minimizing waiting time without any human control. That's what AI for RAN does for radio signals. The final concept is about how AI for RAN enhances overall user experience through end-to-end optimization. When AI operates at both the individual cell and network-wide level, it creates a feedback loop where data flows continuously between layers and locations. The system doesn't just react to issues, it anticipates them. For example, if the network detects that a particular area's user density is increasing due to an event, it can preemptively activate additional base stations or allocate more bandwidth. This level of adaptability ensures consistent quality of service even during peak demand. In technical terms, it improves spectral efficiency, reduces energy consumption, and minimizes delay, all of which contribute to better user satisfaction. It's like having a city that automatically adjusts lighting, transportation, and utilities based on population movement. Users experience faster data rates, fewer dropped connections, and smoother handovers, all without realizing that AI is orchestrating every detail behind. In summary, AI for RAN transforms how radio access networks function by integrating artificial intelligence across both individual and cooperative layers. It enables full-stack acceleration within each cell, optimizes schedulers and channel estimation for greater precision, enhances coordination among neighboring cells for seamless connectivity, and leverages intelligent technologies like carrier aggregation and full duplex for superior spectral efficiency. The network becomes self-aware, adaptive, and predictive, functioning like an intelligent ecosystem that balances resources automatically. For you as future engineers, this represents a new paradigm in communication design, where systems no longer rely on fixed configurations, but evolve dynamically based on data and learning. AI for RAN is not just about making networks faster, it's about making them smarter, turning every base station into an intelligent agent that collaborates to deliver an optimal experience to every user everywhere all the time. Imagine you are driving on a highway using an advanced navigation app. At first, the app only tells you the route, leaving you to adjust speed and direction on your own. Later, it learns from traffic data and starts suggesting alternate paths in real time. Eventually, it becomes part of an intelligent vehicle system that drives itself, coordinating with other cars and traffic lights to prevent congestion altogether. This is exactly how mobile networks are evolving through artificial intelligence and machine learning. They are moving from simple data processing tools to intelligent systems that adapt, optimize, and eventually operate autonomously. Today's topic is how does 3GEP use AI and MLL? The key idea of this slide is that the Third Generation Partnership Project, or 3GEP, is progressively integrating artificial intelligence and machine learning into mobile network standards, making them smarter, faster, and more efficient in managing data, resources, and connectivity from 5G all the way to 6G. All the time. Let us start with the first stage, represented by 3GEP Release 15 and 16, where AI-based functions are applied separately to either user equipment or the network. At this stage, AI is like a personal assistant that helps individual components perform better, but does not yet coordinate across the system. For example, a smartphone might use machine learning to predict signal strength and switch antennas to save battery life, while the network independently uses AI for traffic forecasting or interference reduction. One important development in Release 16 is the introduction of the NWWAF, or Network Data Analytics function, which allows the network to collect and analyze data from various elements to enable automation. Think of NWWAF as a central brain collecting information from sensors spread throughout the body. It provides insights into user behavior, traffic load, and network performance, helping operators make data-driven decisions. While these early applications improve efficiency, they are still limited in scope because the AI systems operate independently rather than collaboratively. Moving forward to Release 17, we enter the stage of AI integration within ENGRAIN and OAM function. Here, AI begins to influence key network operations such as energy saving, load balancing, and mobility optimization. You can imagine this as a city power grid that dynamically adjusts electricity flow based on demand across different districts. Similarly, AI allows the radio access network to distribute resources intelligently, ensuring that busy areas receive more bandwidth while idle regions consume less energy. In OAM, which stands for Operations, Administration, and Maintenance, AI enables what we call zero-touch networks, where maintenance and troubleshooting are automated without human intervention. For instance, if a base station detects signal degradation, the system can self-diagnose and adjust parameters automatically. The concept of Management Data Analytics, or MDA, plays a major role here by providing continuous feedback between network monitoring and AI decision-making module. This stage marks a shift from reactive to proactive management, where the network not only responds to issues, but anticipates and prevents them before they occur. The next major evolution comes with Release 18, where we see the concept of AI collaboration between user equipment and the network. This is the point where AI systems begin to work together instead of operating in isolation. Imagine two musicians who used to perform solos, now learning to play in harmony, adjusting tempo and tone to create a synchronized performance. In technical terms, AI models embedded in user devices start sharing context information with the network, such as motion patterns, application usage, or quality of experience metric. The network, in turn, uses this data to optimize connections dynamically. For example, if a user is streaming high-definition video while moving on a train, the AI on the device can predict handovers between cells, while the network's AI preemptively allocates resources to ensure smooth playback. Another exciting development during this stage is the AI-based NR-Air interface, which introduces use cases such as channel state information feedback, beam management, and positioning. These improvements enhance physical layer performance and reduce latency, enabling ultra-reliable, low-latency communication. This collaboration marks a key milestone toward networks that are context-aware and responsive to real-world conditions. Finally, we arrive at the stage beyond Release 19, which paves the way towards 6G, where AI becomes native in all layers and nodes of the network. This represents the full maturity of AI integration, transforming communication systems into intelligent, self-sustaining ecosystem. In this phase, AI is no longer an external tool, but an intrinsic part of the network's DNA. Every layer, from the physical to the application, uses machine learning models to adapt and evolve continuously. It's like moving from having an AI assistant in each department of a company to having a CEO who is itself an intelligent entity coordinating the entire organization. This stage introduces the concept of native trusted AI, ensuring that algorithms make secure, transparent, and ethical decisions. It also includes advanced features like autonomous systems for energy efficiency, where the network optimizes its power usage across regions and time periods without sacrificing performance. By this point, communication between humans and machines will be seamless, supporting advanced applications such as holographic telepresence, distributed intelligence, and digital twin. The network will learn from its environment, evolve with user behavior, and even repair itself when needed, embodying what we call a zero-touch intelligent infrastructure. When we look at the overall timeline, it becomes clear that the evolution of AI and ML in 3up is a story of growing intelligence and cooperation. It begins with isolated applications that enhance performance locally, progresses to interconnected systems that share data and context, and culminates in a fully autonomous network where AI operates natively across every function. Each stage represents a step closer to networks that are not just reactive, but predictive, not just managed, but self-managing. The journey from 5G to 6G is therefore not only about increasing speed or capacity, but about embedding intelligence into the very structure of communication itself. To conclude today's discussion, 3up's integration of AI and ML transforms mobile networks from passive communication channels into active, intelligent systems capable of learning and decision-making. In the early stages, AI improves specific tasks like data analytics and resource allocation, while later phases introduce collaboration and native intelligence across all layers. By the time we reach 6G, AI will be deeply woven into the fabric of every node and connection, enabling a new generation of autonomous, adaptive, and sustainable networks. For you as future engineers, this evolution means that communication design will no longer focus solely on hardware or protocols, but also on how networks can learn, reason, and adapt in real time. The future of telecommunications is not just about connecting devices. It's about connecting intelligence, creating networks that think alongside us and evolve with the world they serve. Imagine you are managing a large airport. Every day, hundreds of planes arrive and depart. Thousands of passengers move through gates, and countless systems, from security to air traffic control, must coordinate perfectly. If each system operates independently without communication, even a small delay in one area could cause chaos across the entire network. To prevent this, airports rely on centralized data analytics and intelligent coordination systems that predict congestion, allocate resources, and adjust flight schedules in real time. This analogy perfectly describes what AI RAN does within the O-RAN architecture. Today's topic is how does AI RAN work technically within O-RAN architecture. The key idea of this slide is that 3up integrates artificial intelligence and machine learning into 5G systems across multiple domains, management, core, and radio access, to make networks more efficient, adaptive, and self-optimizing. Let us begin with the first point, management and orchestration. In any complex system, coordination is the heart of efficiency, and in 5G, this is handled by what we call Management Data Analytics, or MDA. You can think of it as the brain that analyzes how resources are being used across the network and decides how to allocate them optimally. MDA applies AI and machine learning to large sets of operational data collected from base stations, core nodes, and user devices. It identifies patterns that might be invisible to human operators, such as subtle correlations between user density, signal interference, and power consumption. For example, during peak hours in a busy district, MDA can predict congestion before it happens and reassign bandwidth or activate additional cells to maintain smooth service. It's similar to a smart traffic system that changes traffic light timing dynamically to prevent jams. This proactive management reduces downtime, optimizes performance, and minimizes energy waste. Moreover, it simplifies the operator's job by transforming reactive maintenance into predictive control, ensuring that potential issues are solved before users notice. Next, let's look at how artificial intelligence functions in the 5G core network, specifically through the NWDAF, or Network Data Analytics function. This component serves as the analytical engine of the 5G core, enabling intelligent decision-making across the system. You can imagine WDA-FAS as a data scientist embedded within the network, constantly analyzing performance metrics and user behavior. It collects data such as latency, throughput, and handover success rates, then uses machine learning models to predict network conditions. For instance, if NetDBF detects that a particular region is experiencing fluctuating signal strength due to user movement or weather interference, it can recommend adjustments to base station power levels or suggest optimized routing paths. The result is a self-aware network that continuously learns and evolves based on real-time feedback. From a user's perspective, this translates into faster, more stable connections and fewer dropped calls. In essence, NetWFAF allows the 5G core to act like a living organism, sensing, analyzing, and adapting to its environment dynamically. Now let's move on to the third part, the Next Generation Radio Access Network, or NAU-RAN. This is where AI RAN truly transforms how communication happens at the edge. The radio access network is like the front line of communication, where user devices connect directly to base stations. Traditionally, resource allocation and interference management in RAN are rule-based and static, relying on predefined algorithms. AI changes this by introducing intelligence directly into the radio layer. Through AI and ML, the RAN can optimize coverage, capacity, and throughput dynamically. Imagine it as an adaptive lighting system in a stadium that brightens certain areas based on crowd movement. Similarly, AI RAN can analyze signal conditions and adjust antenna beam patterns, modulation schemes, or frequency allocations in real time to ensure the best user experience. It also enables inter-cell coordination where neighboring base stations share information to prevent interference and enhance overall network harmony. This distributed intelligence ensures that every cell in the network collaborates instead of competing for resources, leading to smoother connectivity and better spectral efficiency. The fourth and final aspect to highlight is how AI seamlessly integrates these layers, management, core, and RAN, into a unified, intelligent ecosystem. In the O-RAN architecture, each layer contributes to a continuous feedback loop. Data flows from the RAN to the core, where WDA and NDA analyze it, and then insights are sent back to the RAN for optimization. It's like a team of doctors monitoring a patient's vital signs, diagnosing issues, and prescribing adjustments instantly to maintain optimal health. This synergy enables what we call closed-loop automation, where the network can monitor, analyze, decide, and act without waiting for human input. Furthermore, this design supports zero-touch operation, meaning that network configurations and optimizations occur automatically with minimal manual intervention. For example, when a new base station is added, AI can analyze its surrounding environment, calibrate parameters, and integrate it into the network autonomously. This reduces deployment time, operational costs, and the likelihood of human error. The collaboration between AI and O-RAN not only enhances technical performance, but also ensures scalability and sustainability as network demands grow. To make this more tangible, think of AI RAN working within O-RAN as a three-tier symphony. The management and orchestration layer is the conductor, ensuring that all parts play in harmony. The 5G core, powered by WDA-FAF, is the composer, constantly analyzing and rewriting the score based on audience feedback. The NE-RAN is the orchestra, performing with precision and agility, adjusting tempo and intensity as the environment changes. Together, they create a performance that is not only efficient, but adaptive, continuously improving through learning. This integration is what allows modern 5G networks to support complex applications such as autonomous vehicles, telemedicine, and smart manufacturing, where reliability, latency, and capacity must be balanced in real time. In conclusion, AI RAN within the O-RAN architecture represents the convergence of intelligence, flexibility, and performance optimization in modern communication systems. Through AI-driven management and orchestration, networks become proactive rather than reactive. The 5G core, with NetApp acts as a powerful analytical engine that learns from data to enhance efficiency and user experience. The next generation RAN applies AI at the edge to dynamically optimize radio resources, ensuring robust coverage and seamless connectivity. Together, these elements form a self-sustaining ecosystem capable of monitoring, analyzing, and evolving without human supervision. For you as future communication engineers, understanding this integration is essential because it defines the future of wireless technology. The networks you will design will no longer be static infrastructures, but intelligent entities that think, learn, and adapt, turning data into decisions and connectivity into intelligence. Imagine a city where every streetlight, traffic signal, and bus operates intelligently. When there are fewer cars at night, some lights automatically dim to save energy. During rush hour, traffic signals adjust their timing dynamically to balance flow, and buses reroute themselves to avoid congested roads. This kind of smart coordination is exactly what AI RAN brings to mobile networks. Just like a smart city manages its resources efficiently, AI RAN optimizes energy, balances load, and enhances mobility in wireless communication system. Today's topic is, how does AI RAN work technically within O-RAN architecture? The key idea of this slide is that 3GEP uses artificial intelligence to make mobile networks more energy efficient, adaptive, and reliable by predicting and optimizing how cells and users behave over time. Let's begin with the first application: network energy saving. In a traditional communication network, all base stations are usually kept active, even during times of low traffic such as late at night. This is like keeping every store in a shopping mall open when only a handful of customers are walking by. AI RAN changes this by introducing intelligence that learns from traffic patterns and predicts when and where energy is needed most. It can recommend activating or deactivating certain cells depending on user demand, weather conditions, or even historical usage data. For example, during weekdays, a business district might require high capacity during office hours, but very little at night. AI can automatically put certain base stations into sleep mode to conserve power, and then reactivate them before the next day's rush begins. This not only saves electricity, but also extends hardware life. Moreover, AI models can evaluate energy efficiency in real time, categorizing cells as active, high, low, or inactive, similar to a power grid that dynamically adjusts generation based on demand. The result is a greener, more sustainable network that intelligently balances performance with resource conservation. Now let's move on to load balancing, which ensures that no single base station is overloaded while others remain idle. Imagine a supermarket with multiple checkout counters. If all customers queue at one counter while others are empty, the process becomes slow and inefficient. AI RAN acts like an intelligent store manager that monitors each counter and directs customers to the ones with shorter lines. In network terms, AI predicts traffic patterns and redistributes users among neighboring cells to maintain equilibrium. It can analyze the resource status of each base station, determining which ones can handle additional users and which are reaching capacity. AI also learns how load fluctuates across time and geography, such as during a sports event or festival, and adjusts coverage accordingly. In addition, AI algorithms can anticipate future demand by examining real-time data, weather, and mobility patterns. This predictive balancing prevents congestion before it happens, leading to smoother connections and better spectral efficiency. Essentially, AI transforms the network into a self-regulating system where workload is shared evenly, maximizing both performance and stability without human intervention. Next, let's talk about mobility optimization, one of the most fascinating applications of AI RAN. Every time a user moves, whether walking down the street or traveling on a high-speed train, their device must switch from one base station to another, a process known as handover. Traditionally, this relies on fixed thresholds, such as signal strength, which can lead to either premature handovers or dropped connection. AI revolutionizes this process by predicting user trajectories based on parameters such as latitude, longitude, altitude, and even speed. Think of it as a navigation system that not only tracks your current position, but also forecasts where you'll be in the next few seconds. By using this predictive capability, AI can estimate which base station will provide the best service in the near future and prepare the connection in advance. It even calculates the probability of successful handover and the ideal timing for execution, minimizing latency. This means that when you stream a video on a moving bus or car, the transition between cells becomes invisible. You never notice a pause or a drop. Additionally, AI can analyze traffic density and resource availability to assign priority to users with critical needs, such as emergency responders or autonomous vehicles. The result is a highly responsive and context-aware mobility management system that keeps connections seamless and reliable. Now that we understand each component individually, let's explore how they interact as a unified AI-driven ecosystem within O-RAN. These three functions, energy saving, load balancing, and mobility optimization, are not isolated tasks, but part of an interdependent feedback loop. For instance, reducing energy consumption by turning off certain cells might affect load distribution or handover performance. AI's holistic view allows it to balance these trade-offs intelligently. It's like an air traffic control system managing hundreds of flights at once, ensuring that every plane lands safely while conserving fuel and maintaining punctuality. AI models within O-RAN continuously gather data from base stations, user devices, and network logs, feeding it into machine learning pipelines that refine predictions and decisions over time. This iterative learning process allows the network to improve itself, becoming smarter and more efficient with each cycle. The integration of AI into O-RAN also introduces a paradigm shift in how networks are maintained. In traditional systems, network engineers analyze performance reports manually and adjust configurations periodically. With AI RAN, this becomes a continuous, automated process. The network monitors itself, identifies potential bottlenecks, and implements optimizations autonomously. For example, if a sudden traffic surge occurs during a public event, AI can activate standby cells, balance user loads across the region, and optimize handovers, all within seconds, without human intervention. This level of automation ensures that users experience consistent quality of service regardless of time, location, or mobility. Moreover, the insights generated by AI models can be shared across the network, allowing different regions to learn from each other. For example, lessons learned from managing traffic in a crowded concert venue could later be applied to a sports stadium in another city. In addition to operational efficiency, AI RAN contributes significantly to sustainability and user experience. By optimizing energy use, it supports environmental goals and reduces operational costs for telecom providers. Load balancing improves fairness and reliability, ensuring that all users receive high-quality connection. Mobility optimization enhances continuity, providing stable communication for applications that depend on uninterrupted data flow, such as autonomous driving, telemedicine, or remote learning. The collective result is a network that is not just faster and smarter, but also more human-centric, designed to anticipate and adapt to the needs of its users. To conclude, AI RAN within O-RAN architecture functions like the brain of a living organism, constantly analyzing, learning, and responding to its environment. It saves energy by turning off unnecessary components, balances workload dynamically to prevent congestion, and predicts user movement to ensure smooth connectivity. These capabilities transform the network from a static infrastructure into an intelligent, adaptive system that continuously evolve. For you, as future communication engineers, This represents the next frontier of design thinking. Networks will no longer be defined only by their speed or bandwidth, but by their intelligence, the ability to sense, decide, and act in real time. The future of telecommunications is not simply about connecting devices. It's about creating networks that think. Imagine standing at the heart of a bustling innovation hub, where engineers, scientists, and business leaders from every corner of the world collaborate to build the next generation of wireless technology. You hear discussions about energy-efficient networks, intelligent automation, and how artificial intelligence will redefine communication. Behind every breakthrough, there are global companies, research institutions, and standardization organizations working in harmony to push technology forward. That is the reality of AI-RAN development today. Our topic is who leads AI-RAN development. The key message of this slide is that AI-RAN's progress is not driven by a single company or country, but by a global ecosystem of technology giants, research organizations, and standardization bodies collaborating to advance network intelligence and automation. Let's start by talking about the contributions of major tech companies. Firms like NVIDIA, Ericsson, Nokia, Huawei, and Qualcomm are at the forefront of AI-RAN innovation. Each plays a unique role in shaping the ecosystem. NVIDIA, for instance, provides the computing backbone through powerful GPUs that accelerate machine learning tasks within network. It's like supplying high-performance engines that allow AI to process enormous amounts of data in real time. Ericsson and Nokia, on the other hand, are the architects of network infrastructure. They integrate AI algorithms directly into base stations and core networks, allowing operators to manage complex systems automatically. Huawei's focus lies in integrating AI for energy saving and resource management, while Qualcomm designs the chips that bring AI capabilities to user devices. Together, these companies form a global orchestra where each contributes a distinct instrument. Some design the hardware, others write the algorithms, and still others set the rhythm for innovation. Their collective efforts establish technical benchmarks and influence how global communication networks evolve. Without these industry leaders setting the pace, the dream of intelligent and adaptive networks would remain theoretical. Now let's explore how their innovations translate into industry standards. When one company invents a new technology, it may only benefit its own ecosystem. But when multiple companies agree on how that technology should operate, it becomes a universal standard that drives global adoption. This is where organizations like 3GAP, EA, and I2 come in. 3GAP, which stands for the Third Generation Partnership Project, is the primary body defining cellular standards, including how AI and machine learning should integrate into 5G 6G system. You can think of 3GAP as the United Nations of Telecommunications, a place where representatives from every major company and research institution come together to decide the technical rules of global connectivity. Similarly, the IEA sets the foundation for communication protocols, ensuring that AI-enhanced systems remain interoperable across different vendors. The ITU, or International Telecommunication Union, complements this process by setting policy frameworks and promoting global cooperation in spectrum allocation. Together, these organizations ensure that the innovations developed by companies are not isolated experiments, but interoperable components of a worldwide network. They transform research into reality by aligning technical goals with commercial and societal needs. Equally important are universities and research institutions, which serve as the innovation laboratories of AI-RAN. Places like the University of Tokyo, Northeastern University, and research centers such as ITRI and URCOM are where many new concepts first emerge. These institutions act as the testbeds where theory meets practice. For example, researchers might develop an AI model that predicts cell congestion in a simulation environment before it is tested in a live 5G network. It's like designing a prototype airplane in a wind tunnel before letting it take flight. Universities also contribute by cultivating talent, training engineers who understand both communication theory and artificial intelligence. These young researchers often bridge the gap between academic exploration and industrial application, translating advanced algorithms into deployable solutions. Moreover, academic collaborations with companies accelerate the innovation cycle. A breakthrough in one lab can quickly be adopted by a corporation and standardized by 3GEP within a few years. This continuous feedback loop between academia and industry keeps AI-RAN development vibrant, fast-moving, and grounded in rigorous research. Let's also acknowledge the importance of cross-industry partnerships and open collaboration. Unlike earlier generations of mobile technology, where a few companies dominated, AI-RAN thrives on shared knowledge and interoperability. Groups like the O-RAN Alliance promote open architectures, allowing equipment from different vendors to work together seamlessly. This openness fosters innovation because companies can focus on specialized components instead of reinventing entire systems. It's similar to building a modern city. One company designs the roads, another develops traffic management systems, while others focus on energy grids and public safety. The city functions because everyone follows the same urban plan. In AI-RAN, this collaborative model ensures that AI modules developed by different organizations can be integrated across diverse hardware and software platforms. For example, an AI model trained by one company to predict signal interference can be deployed within another company's base station hardware, thanks to standardized interfaces. This culture of openness accelerates global progress, reduces costs, and encourages competition based on innovation rather than exclusivity. Now, let's examine the broader influence of these efforts on global networks. As these collaborations mature, they establish not just technical standards, but also economic and strategic leadership. Nations that contribute heavily to AI-RAN research, such as Japan, South Korea, the United States, and European countries, gain an advantage in shaping the direction of global telecommunication. Their companies participate in standardization meetings, propose new frameworks, and even influence spectrum policies that determine how future networks will operate. This is not merely about technology. It is also about global cooperation and competition. The development of AI-RAN symbolizes a new era of technological diplomacy, where countries compete through innovation while also recognizing that interoperability benefits everyone. In this sense, AI-RAN development is both a scientific and a geopolitical endeavor. To tie all of this together, the leadership of AI-RAN development comes from the convergence of industry, academia, and standardization bodies. Tech giants contribute infrastructure and innovation. Standard organizations ensure global alignment, and universities provide the creative spark and technical expertise that drive continuous progress. Each plays a vital role in an interconnected ecosystem that mirrors the networks they are building. Just as AI-RAN integrates intelligence into communication, its development integrates diverse minds and institutions across the world. To conclude, AI-RAN development is a collective achievement built on shared vision and collaboration. Major tech companies like NVIDIA, Ericsson, Nokia, Huawei, and Qualcomm led through research and product innovation, while organizations like 3GEP, EAAE, and I2 established the frameworks that make these technologies globally compatible. Universities and research centers contribute by pioneering new methods and training the next generation of engineers who will shape the intelligent networks of tomorrow. Together, these players transform abstract ideas into concrete solutions that power the future of communication. As future engineers, you should see AI-RAN not just as a technology, but as a model of global cooperation, a demonstration of how innovation, when shared and standardized, can connect the world more intelligently and harmoniously. Imagine a city upgrading from traditional traffic lights to a fully automated traffic system controlled by artificial intelligence. The old system is reliable, predictable, and tested for decades, but it requires manual control and fixed schedule. The new AI system promises smoother traffic flow, better fuel efficiency, and fewer accidents. But it also brings new challenges. different vendors supplying equipment that might not work perfectly together, software updates that could cause malfunctions, and concerns about data security. This is exactly what the telecom industry faces as it transitions from O-RAN to AI-RAN. Today's topic is what challenges will we face moving from O-RAN to AI-RAN? The key idea of this slide is that while AI-RAN offers greater intelligence and efficiency, it also introduces new challenges related to integration, security, and system management that must be carefully addressed to ensure stable and reliable network operations. Let's begin with integration challenges, particularly vendor interoperability. One of O-RAN's biggest strengths, its openness, can also become its greatest weakness when AI is added to the equation. In an O-RAN system, operators can combine hardware and software from different manufacturers, such as base stations from Nokia, AI accelerators from NVIDIA, and management tools from Ericsson. This openness promotes flexibility and competition, but once AI is introduced, compatibility becomes far more complex. Imagine trying to assemble a car using parts from multiple brands. An engine from one company, brakes from another, and an onboard computer made by a third. Each part might work perfectly on its own, but integrating them into a smooth, safe vehicle requires careful coordination. Similarly, in AI-RAN, even slight differences in software interfaces, data formats, or algorithm design can lead to integration issues. If AI models interpret data differently between vendors, the system may allocate resources inefficiently or fail to coordinate signals across cells. These interoperability gaps can reduce performance or even cause network instability. Therefore, the shift to AI-RAN demands a unified framework and rigorous standardization to ensure all components communicate seamlessly, just as international road rules make traffic flow smoothly across borders. The second challenge lies in system complexity. Traditional RANs operate based on deterministic logic, clear rules that govern when and how tasks are executed. Engineers understand exactly how the system will behave under specific conditions. AI-RAN, however, introduces a layer of nonlinearity and unpredictability because its decisions are driven by models that learn from data. It's like replacing a human pilot with an autonomous drone. While the drone may react faster and fly more efficiently, its internal decision-making process is often opaque, even to its designers. In AI-RAN, this black box nature of AI makes troubleshooting difficult. If something goes wrong, engineers can no longer simply trace through code. They must analyze the model's training data and reasoning pattern. Moreover, the growing number of interconnected nodes, each running its own AI module, increases operational complexity. Managing thousands of intelligent agents that continuously adapt in real time requires advanced orchestration and monitoring tools. Without careful management, this complexity could lead to cascading failures where a single misconfiguration propagates across the network, similar to a blackout spreading through a power grid. Thus, while AI enhances autonomy, it also demands new strategies for control, transparency, and explainability. Next, let's talk about security vulnerabilities. One of the most serious concerns in AI-RAN systems. Every time a network becomes more intelligent and interconnected, it also becomes more exposed to cyber risks. In traditional systems, security protocols are well defined and manually enforced. But when AI controls network functions, the attack surface expands because malicious actors can exploit weaknesses in machine learning models or data pipelines. On data pipeline. For example, if an attacker injects false data into an AI model's training set, it could mislead the system into making harmful decisions, like shutting down critical cells or misallocating resources. This is called data poisoning, and it's a growing threat in AI-driven networks. Another issue is misconfiguration. Unlike simple rule-based systems, AI models in O-RAN often require fine-tuning of parameters, and incorrect configurations can cause serious disruption. It's like setting up a self-driving car with the wrong sensor calibration. It might function for a while but fail catastrophically when conditions change. Moreover, automated decision-making introduces ethical and regulatory challenges. Who is responsible if an AI model causes a network outage or security breach? To mitigate these risks, AI RAN systems must incorporate robust verification processes, continuous monitoring, and secure model update. Just as airplanes undergo pre-flight safety checks before every journey, AI models must be regularly audited and retrained to ensure they behave safely and predictably. The next major challenge is data management and privacy. AI RAN depends on massive amounts of real-time data collected from millions of users and devices. This data includes not only network parameters, but also location, usage patterns, and even contextual information like movement trajectory. Managing this volume of information is like trying to drink from a fire hose. You must process it quickly without spilling or wasting valuable insight. The problem is that AI systems need this data to learn and improve, but collecting and storing it introduces privacy concerns. Regulators worldwide, from the US GDPR to Taiwan's Personal Data Protection Act, impose strict rules on how user data can be used. If not handled properly, AI RAN could violate these regulations, leading to legal and ethical problems. For instance, predictive mobility algorithms that anticipate where users are heading could inadvertently expose sensitive information about their daily routines. Furthermore, transmitting this data between different vendors and cloud systems increases the risk of interception. To balance intelligence with privacy, engineers must design AI RAN systems that prioritize anonymization, encryption, and local processing. It's like teaching a student to learn from experience without keeping a diary of private details, understanding the lessons without revealing the source. Finally, we must address the human factor, organizational and skill challenges. Implementing AI RAN requires not just new technology, but also new expertise. Network engineers trained in traditional systems must now learn to work with data scientists, software developers, and AI specialists. It's like asking a team of classical musicians to perform a symphony alongside electronic artists. They must learn to harmonize different instruments and rhythm. The collaboration between telecom and AI disciplines is essential, but not always easy. Organizations must invest in retraining staff and building interdisciplinary teams that understand both communication protocols and AI principles. At the same time, decision makers need to establish governance structures to manage the ethical use of AI, ensuring transparency and accountability. Without these human and organizational adjustments, even the most advanced technology can fail to deliver its potential. To summarize, moving from O-RAN to AI RAN offers tremendous opportunities, but also presents significant challenges. Integration complexity arises from the need to align multiple vendors and systems, while the use of AI introduces new layers of unpredictability and security risks. Data management and privacy concerns add further complications, and the shortage of cross-disciplinary expertise highlights the importance of human collaboration. As future communication engineers, you will not only design the networks of tomorrow, but also safeguard them against these challenges. The success of AI RAN will depend on how well we balance innovation with responsibility, building intelligent systems that are not only powerful, but also trustworthy, transparent, and secure. Imagine you walk into a modern factory that seems to run almost magically. Machines are operating smoothly, materials are moving at just the right pace, and the system automatically adjusts itself when demand changes. Now imagine that this entire operation has a digital mirror, an exact virtual version of the factory that displays real-time data, predicts maintenance issues, and simulates possible improvements before they happen. This is what we call a digital twin, a virtual replica of physical systems that can monitor, analyze, and optimize operations. Today's topic is how we start deploying digital twin service. The key idea of this slide is that deploying digital twin services has become simple, fast, and affordable thanks to cloud technology, standard devices, and easy integration, eliminating the need for costly infrastructure or complex setup. Let us start with the first concept, simple and fast setup. Traditionally, deploying monitoring systems required specialized infrastructure like fixed sensors, beacons, or readers that had to be installed across the facility. This was similar to wiring an entire building for electricity from scratch before you could even turn on the light. But now, digital twin services use real-time location systems, or RTLs devices, which can connect directly to existing networks without the need for such extensive preparation. Think of it as using Wi-Fi to connect instead of laying new cable. These RTLs receivers and devices work together to collect and transmit data in real time, creating a virtual map of the environment. The setup is as easy as installing an app on your phone. It uses the same cloud-based system that other IoT devices rely on, which means it can integrate quickly into existing operations. This flexibility allows companies to deploy digital twins in days rather than months, giving them a fast start toward intelligent monitoring and management. By removing the need for specialized infrastructure, digital twin deployment becomes scalable and accessible, much like how smartphones democratized access to computing power. Next, let's explore how easy integration of devices makes deployment even faster. One of the biggest barriers in older systems was interoperability. Different devices use different communication protocols and required manual calibration to work together. With digital twin services, cloud-based platforms handle this integration seamlessly. It's like having a universal translator that allows devices from various manufacturers to speak the same language. RTL's platforms can connect with standard sensors, embedded systems, and even mobile devices like Android or iOS. Once connected, these devices continuously send location and status data to the cloud, where the digital twin updates automatically. The system can track objects, people, or machines in real time, displaying movements and alerts on a central dashboard. For example, in a warehouse, a digital twin can monitor equipment movement and immediately highlight inefficiencies or safety risks. Because integration is plug and play, companies can add or remove devices easily as their operations evolve. This modular approach means the digital twin system grows with the business instead of requiring an entirely new setup each time. Now let's move to the next point, affordable operation. One of the reasons digital twin technology is becoming widespread is that it uses standard, off-the-shelf devices. In the past, only large corporations could afford the custom hardware and software needed for digital modeling. It was like owning a private satellite just to get aerial images of your property. Today, thanks to cloud computing and standardized IoT devices, the cost of deployment has dropped dramatically. RTL's receivers, cloud dashboards, and edge sensors are mass-produced and can be installed without technical specialists. Moreover, cloud-based software as a service or SaaS platforms allow users to pay only for what they use instead of maintaining expensive local servers. This model offers flexibility and scalability. For instance, a small logistics company can start by tracking a few vehicles and later expand to monitor its entire fleet, all using the same cloud interface. By leveraging shared infrastructure, businesses can reduce capital expenditure and focus on improving productivity. This affordability opens the door for industries of all sizes to adopt digital twin technology, much like how cloud storage replaced costly on-site data centers for individuals and companies alike. Another advantage of cloud-based platforms is that they provide flexibility in deployment environment. Whether the system runs on a public cloud, a private on-premises server, or a hybrid configuration, it can adapt to specific needs. Think of it as choosing between dining in a restaurant, ordering takeout, or cooking at home. The tools are the same, but the experience adjusts to your preference. For sensitive applications such as healthcare or defense, data can stay within local servers to ensure privacy, while less critical operations can utilize global cloud networks for faster updates and analytics. The cloud also simplifies maintenance, since updates, security patches, and AI-driven optimizations happen automatically. This ensures that the digital twin always operates on the latest version of its platform, reducing downtime and technical overhead. Now let's tie these ideas together using a real-world analogy. Deploying a digital twin is like setting up a smart city. The RTL's devices act as sensors embedded in the city, monitoring traffic, air quality, and power usage. The receivers are like control centers collecting all this information, while the cloud platform is the central brain that analyzes and visualizes it. The RTL's dashboard is the city's control room where operators can see everything in real time, from energy consumption to crowd movement. The best part is that none of this requires tearing down old infrastructure. Just as a smart city can evolve by upgrading streetlights and traffic systems without rebuilding roads, digital twins can be added to existing operations without major disruption. This integration of physical and digital systems allows organizations to see not just what is happening now, but also what might happen next, using data-driven prediction to stay one step ahead. Furthermore, digital twins can be tailored for different industries. In manufacturing, they can simulate production lines and detect mechanical faults before they occur. In logistics, they can optimize routes and inventory management. In healthcare, they can create virtual models of hospital wards to monitor patient flow and equipment utilization. All these applications rely on the same foundation: real-time data, connectivity, and cloud intelligence. The simplicity of setup and affordability of operation mean that companies no longer need massive budgets to access these benefits. They only need a clear understanding of what they want to monitor and improve. To conclude, deploying digital twin services is no longer a complex engineering challenge, but an accessible, cost-effective process made possible by cloud technology and standard RTL's devices. The setup is fast because it requires no specialized infrastructure like beacons or readers. Integration is easy thanks to universal cloud platforms that connect diverse devices seamlessly. Operation is affordable because the system leverages standard hardware and pay-as-you-go cloud solutions. Together, these advantages make digital twins a practical tool for industries seeking real-time insight and optimization. As future communication engineers, you will play a vital role in building these intelligent ecosystems. Systems that bridge the physical and digital worlds to make operations not only smarter, but also more sustainable. The digital twin is not just a mirror of reality. It is a tool that helps us understand, predict, and improve it in real time, transforming data into meaningful action across every field of human activity. Imagine you are standing in the middle of Taipei main station during rush hour. Thousands of people are moving in every direction, each with their own destination, each train arriving and leaving within minutes. Now imagine being the system engineer responsible for ensuring that trains run on time, platforms are not overcrowded, and maintenance crews know exactly where to go when something breaks. How would you manage that? Would you rely on CCTV cameras alone, or some sensors scattered here and there? What if you could create a living, breathing digital version of the entire station that mirrors the real one in real time? That is what we call a digital twin, and that is our topic today. So the slide you are looking at is titled, How Digital Twin Supports Positioning. The core message here is that digital twin uses advanced positioning technology and artificial intelligence to manage operations efficiently, predict potential problems before they occur, and optimize the use of resources in real time. You can think of it as a virtual mirror that reflects the physical world with a high degree of precision, continuously updated through data streams. Let's start from the top layer, the AI operations. These are the brains of the entire system. When we talk about AI operations such as passenger flow forecast, optimized work dispatch, and dynamic best route, we are describing how the digital twin interprets the data collected from the physical world. Passenger flow forecast is like predicting traffic on a highway. If the system knows how people move inside a station or an airport, it can predict congestion before it happens. Optimized work dispatch is like a restaurant kitchen during a lunch rush. Orders come in quickly, and the chef must decide which dish to cook first to keep the workflow smooth. The AI looks at available workers, locations, and tasks, then sends the right person to the right place at the right time. Dynamic Best Route is similar to your navigation app adjusting your route when there is a traffic jam ahead. The system recalculates paths dynamically to maintain overall efficiency. Now let's look at predict maintenance needs and sense crowded areas. Predicting maintenance is like a doctor doing preventive health check. Instead of waiting for a machine to fail, the system monitors vibration, temperature, or performance data and predicts when maintenance should be scheduled. Sensing crowded areas is a bit like feeling the pulse of the city. By analyzing data from cameras, Wi-Fi signals, or wearable trackers, the digital twin can visualize where people are clustering and react before those areas become problematic. Optimizing resource plan is the final key in this AI layer. Imagine managing a fleet of buses. Fuel, drivers, routes, and schedules must all align. AI helps determining where to allocate limited resources to achieve maximum efficiency. Now we move to the second layer, the application and system layer, or what we can call the coordination center. Here we have auto allocation, mission, operation planning, third-party applications, operating indicators, emergency response, and customized integration. Auto allocation mission works like an air traffic controller, assigning landing slots to aircraft. The system automatically assigns tasks to workers or machines based on current data, workload, and priorities. Operation planning is the strategic view. It looks at long-term goals and sets daily or weekly plans accordingly. Third-party applications represent the openness of the digital twin ecosystem. For example, a transportation authority might integrate ticketing data or weather information to enrich the simulation. Operating indicators serve as the dashboard gauges of the system, showing metrics like throughput, latency, or efficiency in real time. When an engineer glances at these indicators, they can instantly assess whether operations are running smoothly. Emergency response, as the name suggests, is the system's reflex action. Just as your body automatically pulls back when touching something hot, the digital twin can detect anomalies and trigger predefined responses, like alerting a maintenance team or rerouting passengers. Customized integration is essential because every enterprise has unique needs. A manufacturing plant and a hospital both need digital twins, but their parameters and objectives are very different. The system must be flexible enough to integrate with different sensors, software, and user interface. Moving down to the platform layer, we find two main options: cloud server or on-premises server. Choosing between them is like deciding whether to rent an apartment or own a house. A cloud server is convenient and scalable. You pay for what you use and can expand quickly. But if your data is sensitive or latency must be extremely low, then on-premises might be the better choice because you have full control over the infrastructure. Many organizations use a hybrid approach, balancing flexibility with security. The next layer is the network layer, which is the nervous system connecting everything together. You can choose LoRaWAN as option 1 or cellular networks like 4G LTE and 5G or even Wi-Fi. LoRaWAN is like a marathon runner, slow but enduring. It covers large distances with low power, perfect for sensors that send small bits of data infrequently. Cellular and Wi-Fi networks are sprinters, fast and data hungry, ideal for video feeds or high-volume data. Choosing the right network depends on the trade-off between range, bandwidth, and power consumption. Then we reach the device layer, the sensory organs of the digital twin. These include trackers, watches, personal computers or notebooks, cell phones, CCTV cameras, vehicles, and Wi-Fi dongle. Imagine each device as an eye or ear feeding information into the digital model. A tracker on a worker's badge can tell the system where that person is located. A CCTV camera provides visual confirmation. A vehicle sensor reports its speed and direction. When all these signals converge, the digital twin gains situational awareness similar to how our brains integrate signals from our senses to understand the world around us. Finally, at the bottom is the positioning layer, which provides the fundamental spatial awareness. It includes infraless positioning or hybrid technologies such as iBeacon, ultra-wideband, and RFID. Infraless positioning means using signals already present in the environment rather than installing extra infrastructure. Much like recognizing a street by its landmarks rather than needing a new signpost. Hybrid positioning combines multiple methods to achieve higher accuracy. For example, UB offers centimeter-level precision, while RFID provides inexpensive tracking for assets. Combining them allows the system to handle different scales and accuracy requirements. Now let's link these layers together. Think of the digital twin as a symphony orchestra. The positioning layer is the rhythm section. It keeps everyone in sync. The devices are the instruments generating sounds, or in our case, data. The network is the conductor's baton, ensuring timing and coordination. The platform is the concert hall, providing the right acoustic. The application layer is the sheet music, defining what each musician should play. And finally, the AI operation layer is the composer who designs the entire experience, adjusting melodies and harmonies dynamically based on audience feedback. When all layers work together, the performance, our operational system, becomes both efficient and adaptive. Let's pause for a moment and imagine a practical scenario. Suppose we are managing a smart airport. The digital twin continuously receives data from check-in counters, security gates, luggage belts, and aircraft. It detects that gate C5 is becoming crowded because 2 flights are boarding at the same time. The AI predicts that in 5 minutes, the waiting area will exceed safe occupancy. Instantly, it sends an instruction to open nearby gate 6 as a temporary boarding area and redirects ground staff there. Simultaneously, the maintenance AI detects unusual vibration in a baggage conveyor motor and schedules a technician before it failed. The entire process happens without human micromanagement, and that is the true power of combining positioning technology with AI in a digital twin. From an engineering perspective, the core challenge is maintaining real-time synchronization between the physical and digital layers. Latency, data accuracy, and network stability all matter. That is why communication technologies like 5G and edge computing are becoming key enablers. Edge computing, for instance, allows some decisions to be made locally near the sensors, reducing delay and network load. It is like having reflexes at your fingertips rather than waiting for your brain to decide whether to drop a hot cup. You might wonder where your background in signal and system theory fits in. Remember convolution, filtering, and feedback loops. Those are the same principles used in data fusion and sensor calibration. The digital twin aggregates signals from multiple sensors, each with its own noise and delay, and uses filters, sometimes Kalman filters, to estimate the most likely true state of the system. So in a way, what you learned in signals and systems is the mathematical foundation that makes this high-level coordination possible. As we wrap up, let's summarize. Digital twin supports positioning by creating a continuous feedback loop between the real and the virtual. It senses through devices, communicates through networks, stores and computes through platforms, coordinates through applications, and makes decisions through AI. Each layer depends on the previous one, forming a complete ecosystem. The better the positioning data, the smarter the AI decisions, and the smoother the overall operation. Imagine you walk into a huge shopping mall on a rainy weekend. Your phone's GPS suddenly becomes unreliable, showing you outside the building or even in another block. Yet, an app inside the mall still knows exactly where you are and guides you to the nearest cafe. You might wonder, how can it locate me so precisely without GPS? That question brings us to today's topic, how AI positioning works. The main idea is simple. AI positioning uses existing wireless signals and artificial intelligence models to quickly and accurately predict a user's location. helping applications deliver location-based services without needing any new infrastructure. In other words, we are teaching machines to understand the invisible fingerprints of wireless signals all around us. Let's unpack what this really means. First, AI positioning is simple and efficient. It uses the wireless signals that already exist in the environment, like Wi-Fi, Bluetooth, or cellular signal. No need for new antennas or expensive sensors. Think of it like learning to navigate your own house in the dark. You don't need to install new lights. Your brain remembers the layout, the distance between the sofa and the door, and the sound your footsteps make on different surfaces. Similarly, AI learns the signal patterns that already exist in the air. It analyzes how strong or weak each signal is at various locations, forming a kind of map, what we often call a radio fingerprint map. Every place has its own unique signature, just like how every human has unique fingerprint. Once the AI has learned this fingerprint, it can later recognize your position simply by reading the current signal pattern. Now, why is this method so efficient? Because it quickly learns signal patterns to predict locations. Imagine a musician who can play a song after hearing it only a few times. The AI system does something similar. It collects data about signal strength and patterns, then trains itself to recognize the relationship between those patterns and physical location. The next time it senses a similar combination of signals, it can infer with surprising accuracy where the user is. This process relies on models similar to what you've learned in signal processing, such as pattern recognition and correlation. The system identifies which signals match the stored patterns, much like a matched filter in communications that identifies the right symbol from noisy data. Let's take a real-life analogy. Suppose you often visit a bookstore. You may not remember every shelf, but you recall that near the coffee machine, the smell of espresso is strong, the floor feels smooth, and there is jazz music playing softly. Your brain uses all these cues to know where you are without seeing any signboard. AI positioning does exactly that, except it uses wireless signals as the cues. It combines information from multiple sources, Wi-Fi, Bluetooth, maybe even cellular base stations, to triangulate or estimate your location. The beauty is that all these signals already exist for other purposes, such as communication or data transmission, and AI simply uses them. Now we move to the second part, cost-effective and accurate. Traditional indoor positioning systems often require special hardware like infrared sensors, ultra-wideband anchors, or beacons installed everywhere. That adds cost, complexity, and maintenance burden. AI positioning, in contrast, reduces the cost of extra hardware installation. It's like turning something you already own into a new tool. Think of how smartphones replace so many gadgets, cameras, GPS devices, even flashlights. Similarly, AI positioning transforms existing networks into location sensors without needing to add physical devices. You may wonder, how accurate can such a system be without extra hardware? Surprisingly accurate, even indoors. AI models can handle the nonlinearities and reflections that usually confuse traditional positioning algorithms. Indoors, radio signals bounce off walls, ceilings, and furniture, creating a complex environment known as multipath propagation. To a conventional system, this is like trying to listen to one voice in a noisy crowd. But AI treats this complexity as information. It learns from those patterns of reflections, using them as hints rather than disturbances. You can think of it as a person learning to recognize a friend's voice not by filtering out the noise, but by knowing how that voice sounds when mixed with echoes and background chatter. Let's connect this to your background in signals and systems. Remember how we studied impulse responses and convolution. In a sense, each environment has its own impulse response to radio signals. When a signal is transmitted, it gets convolved with the environment's characteristics. The AI model learns that mapping indirectly by observing many examples without having to compute it analytically. It's a data-driven version of what we used to describe mathematically. The more data it gets, the better it understands how signal patterns translate into positions. The images on the slide illustrate this process. The colorful circular maps represent signal strength distributions in different areas. Each color corresponds to a unique combination of wireless signal features. The AI takes this information and turns it into a predictive model. On the right, you can see a smartphone running an AI positioning app. It doesn't measure distance directly like a laser. Instead, it senses the environment through its wireless receiver, compares the observed pattern to its learned model, and outputs the estimated position. The middle photo shows the real-world testing environment, people moving around, signals fluctuating, and yet the system continues to locate devices with impressive stability. So, how does the AI actually learn? It usually starts with a training phase, where the model collects labeled data, meaning it knows both the signal patterns and the corresponding true position. This is similar to supervised learning, which some of you might have encountered in machine learning courses. The model builds an internal representation of how signals vary across the area. Later, in the prediction phase, when it receives a new set of signals without knowing the true position, it compares them to what it has learned and predicts the most likely location. Over time, it can even adapt to environmental changes, such as new furniture or rearranged equipment, by continuously updating its model. This adaptability is one of the major strengths of AI-based systems compared to static algorithms. Let's reflect on the phrase simple and efficient once again. AI positioning makes use of what's already there, learns autonomously, and provides results quickly. It is similar to a student who, instead of memorizing every formula, understands the concept so deeply that he can solve new problems just by reasoning through familiar patterns. That's the essence of intelligence, learning from examples and generalizing to new situations. And the phrase cost-effective and accurate captures the practical advantage. In real-world engineering, performance is not just about precision, but also about scalability and cost. You could always install more hardware to get better accuracy, but AI gives us a smarter way. It's like upgrading software rather than replacing machines. You spend on computation and data rather than on physical installations, making deployment faster and cheaper. As we reach the end of this discussion, let's put everything together. AI positioning works by turning the invisible chaos of wireless signals into meaningful spatial information. It listens to the electromagnetic whispers in the environment, and through learning, translates them into precise location estimate. It achieves this without new infrastructure, without extra hardware, and with continuous self-improvement through data. For engineers like us, this represents a paradigm shift. Instead of building more sensors, we extract more intelligence from what we already have. To summarize, AI positioning is the art of teaching machines to sense the world through the existing wireless landscape. It is simple and efficient because it ruses available signals and learns patterns automatically. It is cost-effective and accurate because it avoids expensive installations while delivering precise results, even indoors where traditional GPS fails. And beyond the technology itself, it reflects a larger principle that applies to all of engineering. Sometimes progress doesn't come from adding more things, but from understanding better what's already around us. That, I believe, is the real beauty of AI positioning. Imagine you are visiting a large hospital for the first time. You walk into the lobby, and immediately your phone shows you the exact route to the radiology department, even indicating which elevator to take. No one installed new sensors just for this feature, yet it works seamlessly. This convenience is made possible by AI positioning technology, which has evolved to be not only powerful, but also extremely easy to deploy. Today, we will explore the topic shown on the slide. What are AI positioning features? The key point is that AI positioning provides affordable, easy-to-use, and accurate location predictions by using existing wireless signals and simple integration methods, making it suitable for almost any building or device. Let us begin with the idea of being easy to set up and use. Traditional indoor positioning systems often required complicated calibration, multiple hardware installations, and long configuration times. But AI positioning flips this experience completely. It can be quickly set up across multiple buildings or floors using only the wireless infrastructure that is already in place. Imagine setting up a Wi-Fi router at home. Once you plug it in, all your devices immediately recognize the signal and connect. AI positioning works with a similar simplicity. It does not demand a specialized technician to spend days tuning sensors. Instead, the system learns the environment using the wireless signals already present, such as Wi-Fi or Bluetooth. It's like teaching a new student to navigate the campus not by building new roads, but by letting them walk around a few times and memorize landmarks. Another strength is that AI positioning easily integrates with other systems using standard software. Think of it as a universal translator. Whether it's a hospital management system, a smart campus application, or a retail analytics dashboard, AI positioning can communicate and share data through open interfaces and API. In more intuitive terms, it behaves like a skilled interpreter who can talk fluently to both engineers and administrators, ensuring that the positioning information flows smoothly into the systems that need it. This integration is crucial because location data alone is meaningless unless it is connected with operational systems that can act on it. When the AI positioning engine reports that a crowd is forming in one area, for example, the facility management system can automatically adjust air conditioning or lighting to maintain comfort and safety. Now let's move on to the real-world success of AI positioning. It has already been successfully used in hospitals, schools, and shopping centers. These are complex and dynamic environments filled with moving people, walls, and interference sources. Yet AI positioning performs remarkably well because it continuously learns and adapts. In hospitals, it helps locate medical equipment and patients efficiently. Imagine a nurse looking for an infusion pump. Instead of walking through several wards, she simply checks the tablet and sees the real-time location. In schools, it can monitor student flow for safety or guide visitors during open house events. In shopping centers, it enables indoor navigation and targeted promotion. You might get a message that a sale is happening right in the store next to you, all thanks to precise indoor location tracking. Compatibility is another major feature. AI positioning works with many types of devices such as phones, tablets, and cameras. That universality is similar to how USB ports became the standard for connecting devices. Before USB, every device had its own connector, and compatibility was a nightmare. AI positioning aims for the same simplicity. No matter what kind of device or operating system you use, as long as it can receive wireless signals, it can participate in the positioning network. For engineers, this means scalability. You can start with a small deployment, say in one building, and then expand across an entire campus without changing the hardware. Let's connect these points conceptually. Easy setup means lower deployment barriers. Easy integration means interoperability. Real-world success means proven reliability. Compatibility means future scalability. Together they make AI positioning not just a laboratory technology, but a practical solution ready for daily use. From a communication engineering perspective, what makes this possible is the convergence of signal processing, network communication, and machine learning. The system takes raw signal data, analyzes patterns, and transforms them into actionable spatial information, all while maintaining minimal setup complexity. If we think back to the fundamentals you learned in signals and systems, you might recall the concept of system response. In essence, every building reacts to wireless signals differently, producing a unique pattern. AI positioning learns that response pattern, which is like identifying a person by recognizing their voice timbre. Once the pattern is known, the system can instantly recognize the same environment anywhere else. This ability to generalize across spaces and devices is what makes AI positioning easy to replicate and scale. To visualize this, consider the circle diagram shown on the slide. It symbolizes the seamless cycle between integration, computation, and hardware. At one point, AI learns and processes data. At another, standard software interfaces allow communication with other systems. At yet another, Simple hardware deployment enables expansion to new sites. It's a self-sustaining ecosystem where each part supports the others to keep the system efficient and flexible. Let's use a simple analogy to tie everything together. Imagine AI positioning as a talented orchestra. The existing wireless signals are the instruments, already tuned and ready. The AI model is the conductor, interpreting the melody of data to create harmony. The integration software is the concert hall that connects the music to the audience. The result is a symphony of technology that transforms ordinary wireless signals into meaningful positioning intelligence, bringing order and insight into complex environments. To wrap up, the features of AI positioning can be summarized in two ideas: simplicity and universality. It is simple because it uses what already exists and learns quickly with minimal effort. It is universal because it can integrate into any building, work with various systems, and support a wide range of devices. Whether in a hospital tracking medical assets, in a school guiding students, or in a shopping center enhancing customer experience, AI positioning proves its value through real-world success. As communication engineers, understanding this technology reminds us of an important lesson. Innovation often comes not from adding more components, but from discovering smarter ways to use the signals and systems already surrounding us. Imagine yourself standing at Changi Airport in Singapore, one of the busiest and most efficient airports in the world. Every minute, thousands of passengers move through its terminals. Wheelchairs are being pushed, trolleys are being returned, and ground staff are coordinating flights with precision. Now, imagine trying to manage all of that movement manually. It would be like trying to conduct an orchestra blindfolded, with every musician playing on a different tempo. Today, we will discuss how AI positioning solved this challenge in a real-world case study at Singapore Changi Airport. The key point of this slide is that Changi Airport adopted AI positioning to track staff and assets, enhancing efficiency and visibility while significantly reducing costs compared to traditional management methods. Let's begin with the first part, real-world success. The system was successfully deployed across all Changi Airport terminals. Think about what that means. Each terminal is like a small city with its own transportation routes, service zones, and timing schedule. Deploying AI, positioning across all of them, is equivalent to giving each city its own real-time traffic control center. This system tracks everything that moves, from staff to service vehicles, ensuring that every operation runs like clockwork. Proven cost savings and operational improvements were recorded, which demonstrates that technology is not just a luxury, but a practical investment. The airport could reduce unnecessary manpower while improving accuracy in operation. It is similar to upgrading from paper maps to GPS navigation. Once you can see everything clearly, you make better decisions and waste fewer resources. Next, we move to the second part, asset and staff tracking. The airport uses AI position to efficiently manage wheelchairs, buggies, e-caddies, and staff movement. Let's think about a wheelchair as a moving node in a network. Without tracking, the system doesn't know where the node is at any moment. When a request comes from a passenger who needs assistance, staff would have to search manually, wasting valuable time. But with AI positioning, each wheelchair's location is updated in real time, just like how your phone constantly updates your position on a map. The control center can assign the closest available wheelchair and attendant, reducing waiting time for passengers. The same logic applies to buggies and trolleys. It's like a delivery platform where the system knows which driver is nearby and available, and automatically assigns the task based on proximity and availability. Now imagine the scale of this coordination. Hundreds of staff members and thousands of equipment items are moving simultaneously across large spaces. Without a centralized view, it's nearly impossible to manage efficiently. AI positioning provides that bird's-eye view, merging all movements into one digital model. It's like watching an air traffic control radar, but instead of tracking airplanes, it tracks every ground operation asset in real time. The airport staff can see whether there are enough wheelchairs near arrival gates, whether buggies are distributed evenly, or whether certain zones need reinforcement. This visibility turns chaos into coordination. One particularly impressive outcome is the clear improvement in service quality and resource allocation. Passengers experience smoother assistance, and staff no longer waste energy searching for missing equipment. Think of it as switching from reactive management to predictive management. Previously, if a buggy broke down or got misplaced, it would take hours before anyone noticed. Now, AI systems detect inactivity or abnormal patterns immediately. It's like a fitness tracker that alerts you when your heartbeat deviates from normal. It doesn't wait for something to go wrong before responding. Let's take a closer look at why this deployment works so well at an airport. From an engineering perspective, an airport provides an ideal testbed for AI positioning because it is a highly structured yet dynamic environment. Wireless signals are abundant, from Wi-Fi to cellular networks, and objects move in predictable patterns. Staff follow routines, vehicles follow paths, and passenger flows follow schedule. The AI model can therefore learn signal patterns quickly and predict positions with high accuracy. In practice, the positioning engine is embedded in devices such as smartphones carried by staff, turning them into intelligent sensors. These devices continuously sense signal patterns, report data, and receive instructions. It's a distributed intelligence system where every node contributes to the overall situational awareness. Another key advantage is that this system integrates smoothly with existing airport infrastructure. No need to install new antennas or redesign the network. It uses the wireless environment already in place, much like how autonomous vehicles use the same roads as regular cars. This not only saves cost, but also ensures faster deployment. The airport did not need to halt operations or rebuild facilities. The technology simply blended into the workflow. From a human perspective, this project also highlights the collaboration between technology and people. Some worry that automation replaces human jobs, but in this case, it enhances them. Staff are freed from repetitive searching or reporting tasks and can focus more on serving passengers. You can think of AI positioning as a smart assistant that handles logistics while humans handle empathy. It's the perfect example of how communication technology and artificial intelligence can improve both efficiency and human experience. Now, let's connect the engineering side to what you have learned in signal and system theory. Every moving asset generates a time-varying signal profile, like a waveform evolving over time. The AI model analyzes these signals across multiple frequencies and access points, performing a kind of pattern recognition that resembles convolution operation. Instead of filtering noise from a communication channel, it filters uncertainty from the location data. The result is a clear, stable estimation of position that updates continuously. Just as a well-designed filter produces a smooth output despite noisy input. To visualize the impact, think of the airport before and after adopting AI positioning. Before, each operation was like an independent puzzle piece handled by different teams with limited visibility. After deployment, it became a complete picture where every movement from wheelchairs to staff patrols is interconnected. This is the transformation from disconnected data to integrated intelligence. And that's the true value of AI positioning. In summary, the Changi Airport case study demonstrates how AI positioning can revolutionize large-scale operation. It has proven success across all terminals, achieved measurable cost savings, and optimized both asset and staff tracking. The system efficiently manages wheelchairs, buggies, and staff movements while improving service quality and resource allocation. Most importantly, it shows that by merging AI, communication signals, and operational data, we can build environments that are not just smart, but adaptive. So next time you walk through an airport and everything seems effortlessly organized, remember that behind that calm surface is an invisible network of signals and intelligence working just as elegant as any communication system we study in this classroom. Imagine you just arrived at Bangkok Suvarnabhumi Airport for an international flight. It's crowded, signs are confusing, and you're unsure which gate to head to. Yet your phone suddenly shows a clear path with arrows guiding you in real time, smoothly leading you to your gate. This is not magic. It's AI positioning at work. Today's topic, the case study for BTK Airport passenger navigation, shows how AI positioning replaced faulty beacon systems to give travelers accurate and reliable indoor navigation, greatly improving their experience. Let's start with real passenger improvement. The key success here is that passengers can quickly and easily find their way through the airport. It's like having a personal guide who always knows where you are, even in a maze. Traditional beacon systems often failed because they depended on small hardware devices that could lose power or go out of sync. But AI positioning doesn't need those beacons. Instead, it learns signal patterns from existing Wi-Fi or cellular networks and calculates your position like a skilled detective piecing clues together from subtle hints. This makes navigation seamless and automatic, allowing passengers to focus on travel instead of wandering in confusion. Positive feedback from travelers confirms that the system greatly improved wayfinding performance. Think of it as switching from an outdated paper map to a live digital compass that updates instantly as you move. Passengers appreciate that they no longer get lost between terminals or misread confusing signboards. In an environment as large and busy as an airport, this improvement transforms the passenger experience from stressful to effortless. Now let's consider why the traditional beacon system failed. Beacons couldn't operate reliably because of interference, battery issues, and maintenance needs. Imagine relying on a set of candles to light a large hall. They can flicker, burn out, and require constant attention. Replacing them with electric lights, however, provides stable illumination with far less effort. That's the difference AI positioning made. By eliminating a need for beacon maintenance, the airport reduced operational costs while improving reliability. This shift represents a broader engineering principle. When you replace hardware dependency with data intelligence, systems become more scalable and resilient. The photo on the slide shows an example of AI positioning in action. A smartphone running an indoor navigation app uses signal patterns to guide the passenger, with the route displayed clearly on screen. The map updates as the traveler walks, giving real-time feedback, just like GPS, but designed for indoor use. In essence, the phone becomes both sensor and navigator, using AI to interpret its wireless environment without relying on external anchors. From an engineering perspective, this is a fascinating application of signal processing and pattern recognition. The AI model continuously analyzes signal strength variations and compares them with learned environmental patterns to estimate location. This is similar to how your brain uses both memory and perception to navigate familiar spaces. Each step updates the model's estimate, like a feedback control system, refining its output with every new measurement. The success at BTK Airport demonstrates the maturity of AI positioning technology. It proves that advanced algorithms can outperform traditional beacon-based systems in accuracy, cost efficiency, and user experience. It also highlights how communication engineering has evolved beyond connectivity. Now, we use wireless signals not only to transmit data, but also to sense and interpret the environment itself. To summarize, AI positioning at BTK Airport provides precise, reliable passenger navigation by replacing beacon systems with intelligent signal-based models. It helps travelers find their way faster, eliminates hardware maintenance, and offers smoother, stress-free airport navigation. In short, this case study shows how data-driven intelligence can transform even the simplest human task, finding your way into an elegant example of applied communication engineering. Imagine walking into a modern factory filled with machines, conveyors, and workers moving constantly. In such a complex environment, knowing where every asset or worker is in real time can make the difference between smooth production and costly downtime. Now imagine achieving that without installing new sensors or cameras. That is the power of AI positioning in manufacturing. Today's topic, The case study for manufacturing demonstrates how factories use AI positioning for mobile asset tracking and AR patrol applications, reducing costs and improving efficient infrastructure and expensive image recognition systems. Let's start with the first point: no extra infrastructure. One of the most impressive aspects of AI positioning is that it uses existing wireless signal. Instead of deploying new antennas, cameras, or beacons, the system learns to interpret Wi-Fi, cellular, or Bluetooth signals already present in the factory. Think of it as learning to navigate your own home in the dark. You don't install new lights every time. You rely on memory and the spatial cues that already exist. Similarly, AI positioning recognizes the signal environment and maps it intelligently, transforming invisible radio waves into spatial awareness. This eliminates the need for new hardware installations, which traditionally were both time-consuming and expensive. Saving money compared to traditional positioning technologies is another major benefit. In the past, indoor tracking relied heavily on image recognition or RFID systems, both of which required costly equipment and regular maintenance. AI positioning replaces these with software intelligence. It's like replacing a fleet of expensive security guards with a single smart camera that understands patterns and movements on its own. By using what's already available in the wireless environment, factories can achieve the same, or even better, accuracy without the recurring cost of upkeep or recalibration. Now, moving to the second point, improved operational efficiency. Modern factories are complex ecosystems, and AI positioning enhances efficiency by integrating with our patrol application. These applications allow supervisors to walk through the factory while receiving live visual data on their devices. Through augmented reality, they can see the location and condition of machines or spot anomalies immediately. Imagine walking through a warehouse wearing AR goggles, and as you pass each machine, a digital tag pops up showing its temperature, status, or maintenance schedule. This creates a bridge between the physical and digital worlds, often called the digital twin. The digital twin acts as a real-time reflection of the factory's operations, giving engineers a comprehensive view of both assets and personnel. Accurate positioning further enhances patrol effectiveness and management. When a worker uses a body camera or mobile device equipped with AI positioning, the system knows exactly where the recording is happening. This is like having a GPS for the indoor environment, ensuring that every inspection record is linked precisely to its physical location. If an incident occurs or a defect is found, managers can trace it back instantly. It's similar to having a playback of a soccer game, where you not only see what happened, but also exactly where on the field it took place. This level of spatial accuracy improves accountability and speeds up troubleshooting. Looking at the diagram on the slide, we see a network of IoT user equipment, such as phones, our goggles, body cams, and tablets, all connected through a 5G or Wi-Fi network. These devices gather data from built-in sensors like accelerometers, gyroscopes, magnetometers, and barometers. You can think of them as a team of scouts, each reporting their observations to a command center. The 5G private network station, shown on the right, acts as that command center, collecting signals, processing them, and delivering precise location data. This architecture ensures low latency and high reliability, essential for real-time industrial operations. From an engineering point of view, this system is a beautiful application of communication principles you already know. Wireless signals carry both data and contextual information about the environment. Variations in signal strength, phase, or timing can all be analyzed to estimate position. The AI model serves as an adaptive filter that learns these patterns over time, refining its predictions as more data comes in. This is the same concept as a feedback system in signal processing, continually adjusting its output to reduce error. In practice, this leads to measurable gains in productivity. Patrol cycles become faster, downtime is reduced, and safety compliance improves. When equipment or tools are misplaced, the system can locate them instantly. When operators patrol the line, our guidance ensures no area is missed. The overall workflow becomes proactive rather than reactive. It's the difference between driving with headlights that only illuminate what's in front of you and having a radar that tells you what's coming next. Moreover, this approach supports scalability. Once the AI model has learned the signal characteristics of one area, it can easily expand to another building or production line. There is no need to redo wiring or calibration, making the system flexible for future factory expansion. It adapts to environmental changes like rearranged machinery or added equipment, much like how your phone's navigation adjusts when roads are under construction. To conclude, the case study for manufacturing shows how AI positioning transforms industrial operations by removing the need for extra infrastructure and boosting efficiency through real-time data and our integration. It replaces expensive hardware with intelligent software, connects digital twins with human patrols, and provides precision management for assets and workers. In essence, it turns the factory floor into a living learning environment, one that senses, adapts, and optimizes itself using the very signals that already fill the air. This is the future of industrial communication, where intelligence replaces complexity and connectivity becomes the foundation of every smart operation. Imagine walking into a hospital emergency room during a busy evening. Nurses rush between patients, carts filled with monitors and medicine move constantly, and doctors need specific equipment immediately. Now, imagine one of those crucial devices goes missing or is misplaced. Every minute spent searching could delay treatment. This is where AI positioning changes everything. Today's topic, the case study for healthcare, shows how hospitals use AI positioning in medical PCs to track equipment, manage nursing carts, and analyze data, all without installing extra hardware. The result is faster operations, better patient care, and lower costs. Let's start with the first part, efficient equipment tracking. In a hospital, time is the most valuable resource. When AI can quickly locate important medical equipment, it's like having an invisible assistant that always knows where everything is. Instead of staff manually checking each room, the system continuously monitors the location of medical carts, monitors, and devices using existing wireless signals such as Wi-Fi or Bluetooth. Imagine how you use your phone's map to locate a friend in a crowded festival. AI positioning does the same, but instead of people, it tracks equipment moving around the hospital. This real-time visibility saves enormous effort and prevents delays during emergencies. Another advantage is that no extra hardware is required, reducing installation and maintenance costs. Traditional tracking systems often rely on sensors or beacons placed around the facility. These require setup, calibration, and constant maintenance. It's like running a restaurant where every table has its own small lamp. You need to keep replacing bulbs and batteries. AI positioning, on the other hand, uses the ambient wireless environment that already exists, much like cooking, with ingredients already in your kitchen. This not only saves money, but also simplifies deployment. The hospital doesn't need to shut down areas or install complex systems. The technology simply integrates into existing networks and starts learning signal patterns immediately. Now we move to the second point, enhanced operational management. Beyond just locating equipment, AI positioning also collects data that can optimize nursing operations. Think of it as turning the hospital into a living system that can analyze its own rhythm. For example, by tracking how carts move through wards, the AI can identify bottlenecks or overused corridors. It's similar to how traffic engineers analyze vehicle flow to design better roads. In this case, data analysis helps allocate resources more effectively, whether that means adjusting staff schedules, reorganizing equipment storage, or improving patient flow. Real-time alerts are another powerful feature. When something unusual happens, like a device leaving a restricted area or a delay in equipment delivery, the system immediately notifies staff. This is like having a smart security system that doesn't just record events but actively warns you when something is off. For nurses, this means being able to respond faster to patient needs. If a vital sign monitor is needed in room 5, the system instantly shows the nearest available one. eliminating unnecessary movement and saving time. Let's take a closer look at how this system operates behind the scenes. The AI algorithm continuously analyzes the patterns of wireless signals interacting with medical PCs cart. Each location in the hospital has a unique signal signature, similar to how every person has a distinct fingerprint. The AI learns these signatures through training and uses them to infer precise positions later. This is the same principle you learned in signal and system theory, where we identify a system's response based on input and output relationship. Here, the environment acts as the system, and the wireless signals serve as inputs that reveal spatial information. Looking at the images on the slide, we can see a medical professional pushing a nursing cart equipped with a computer. That cart is not just a workstation, it's part of a smart network. As it moves, the AI tracks its position and updates a digital floor plan shown in the bottom image. This digital map acts as a dynamic interface for managers to monitor activities in real time. It's like watching the hospital as if it were a control panel in an airplane cockpit where every instrument is visible and constantly updated. This system also enhances collaboration between teams. Maintenance staff know which equipment is due for inspection, logistics teams know where supplies are, and nurses can focus on patients instead of logistics. It transforms daily routines from reactive to proactive. Instead of searching when something goes missing, the system prevents the loss from happening in the first place. It's the difference between putting out fires and having smoke detectors that warn you early. From a communication engineering perspective, this case study highlights the growing importance of intelligent wireless network. The same signals that carry data are now being used for spatial sensing. The line between communication and sensing is blurring, creating what we call perceptive network. This is a beautiful example of how abstract signal theory translates into practical, life-saving applications. The hospital becomes not just connected, but aware. To sum up, the case study for healthcare demonstrates how AI positioning revolutionizes hospital operation. It enables efficient equipment tracking by using existing wireless signals, requiring no extra hardware and minimizing cost. It also improves operational management through data-driven analysis and real-time alerts that enhance patient care. By merging AI, signal processing, and wireless communication, hospitals can operate more intelligently, ensuring that every second and every device count. In the end, this technology does more than just locate equipment. It gives healthcare professionals the one resource they need most: time to care for patients.